Good evening, everyone. We are in the week 6 problem solving session of the course, Digital Control in Switch Mode Power Converters and FPGA-based Prototyping. And week 6 is about Digital Control Implementation and FPGA-based Prototyping. Okay, let me share my screen. Full screen. Is my screen visible?
Yeah.
Okay. So we are in the week 6 of this course, which is about digital control implementation and FPGA-based prototyping. So before we go into week 6, I just want to give a summary about week 5. So in week 5, we have learned about the digital control. So mainly in the digital control, how are we designing the controller? So we have discussed about the controller design. These are the main aspects that we have discussed in the week 5. So S domain to Z domain. So if you go here, so just to summarize, we have discussed with continuous time to discrete time transformation. So there are 3 different transformation: forward, backward, and bilinear. And we have derived the stability expressions, and we have realized that forward we cannot use. We can either use backward, or we can either use bilinear transformation when we are doing from S to Z. So that is our conclusion. And coming to the next discussion, we have discussed about the PID tuning of voltage mode control bar. So in analog, we have used the continuous time model, and in digital, we have discussed multiple times. We have used continuous time with delay, which would be sufficient to design a controller. Same with the PID tuning of current mode control. Here we have used continuous time model. Here we have continuous time with delay. So with the TAUD model additional, which will affect only the phase margin, others will be exactly same as analog. Then we have discussed something about large signal tuning, which is the trajectory based controller tuning. So even if you face some difficulty in understanding this, it is still okay, because you might not exactly understand the entire derivation, which is a bit high level. So we will not be asking questions on derivation, more like you can use the result to tune your controller. So we will be mainly like questioning you in the terms of implementing it in, like, are you actually understanding how to use the results in designing the controller? So our main intention is that. But if you want to understand the proof of this thing, then you are free to go through the previous lecture. But even if you do not understand, it is still okay. And then we have solved a few problems on controller designing of PI, of current mode control. Both small signal model as well as large signal tuning. So how do what are the values of KPKA in small signal if you go small signal model, and what are the values of KPKA when we use large signal model. So that is all about week 5. So now coming to week 6.
Hello.
Yes.
Yeah, actually, on the day you told me to remember why the PFM is used in like the DC mode.
Yes. So yeah, I forgot. Thanks for reminding. So what happens is, maybe I can use this space. Let me select a light color. So what happens is, say we have inductor current of say 1 ampere. So the ripple is like this, right? So the average is 1 ampere. So this is the inductor current. Say the ripple is delta IL, say 20% of 10 amperes. So it is how much? Okay, then it would be somewhat high. So let us say 0.5 amperes is the ripple, 0.5. Now the load requirement got reduced, and the inductor current has become, say, we need only 0.1 ampere. So the average is 0.1. So this is the average 0.1. And across it, the ripple will be 0.5. So the ripple is 0.5. So in this case, delta IL is 0.5. And average inductor current is 0.1 ampere, because the load requirement has reduced. Now, if you actually calculate the losses, we'll calculate losses as IRMS square into, say, the DCR RL, right? We are considering the conduction losses. So we are considering the conduction losses of RL. There will be R on as well. So it will be like either on time or off time of IL. So for simplicity, let us consider RL. Because of this ripple, this I am, yes.
Sir, if we consider like this, then the ripple is almost 500% of.
No, there are two things. See, when we design delta IL is based on 20% of the IL maximum. So whenever you design IL, you consider delta IL is 20% of the IL maximum. Say IL maximum is 20 amperes. Then you consider 20% of this maximum current. Say delta IL, I am considering say 0.5 amperes. So say my IL maximum is 2.5 amperes, right? So this is 20%, right? Is my calculation correct? 1/5. Yes.
Yes.
Yeah.
Yes.
So we have designed considering IL max, keeping IL max in
Usually
mind.
we will say.
Yes.
Sir, usually we will say from the average current only the ripple. From
Yes.
average current we will say
No.
percentage.
When we are designing, actually when we are actually designing delta IL thumb rule is 20 to 30%. So, but 20 to 30% of what? 20 to 30% of IL maximum. So if the maximum current is 20 amperes, then then we can go to delta IL of 20% of 20 amperes. So that is the thumb rule that we keep in mind. Similarly, in this case, I have considered delta IL max to be 2.5 amperes. Understood?
Understood.
So delta IL is 0.5 amperes. So for designing purpose, my delta IL is 0.5 amperes. But even if I reduce IL, say now, as you have pointed out, a very good thing. See, my IL is 0.1 amperes, but my ripple is more because I have designed it for the worst case scenario. Now what happens because of this ripple, my losses will increase. So what people do, because when IL is becoming lesser and lesser, the average value is less, but ripple is more, right? As you have pointed out, it is 5 times, which it should not be. So they use different light load architectures. There are different light load architectures. So they operate usually in DCM. DCM means discontinuous conduction mode. So inductor current will be discontinuous. Say it will be like this. So majority of the time it is off, and the peak depends upon the average current. Say it is operating in fixed frequency. This is FHW. And say this time is some X, and I peak is I peak, right? So if I take average of time period into I peak by total time period is the average, right? So it is the delta IL. So if my delta IL decreases, then this peak will decrease because the average should decrease, right? Have you understood? Hello.
Yes.
Yes. So in this case, I am not allowing my inductor current to have this much ripple. Rather, there are again different ways. So one, you can actually fix I peak so that the duty ratio will be accordingly adjusted. So you can put a very small I peak, and accordingly the duty ratio will be adjusted. So delta L is fixed. Delta L now it will not be anymore 0.5 amperes. Rather, it will be the value that we have selected to fix it. So now it is becoming 0 and the ripple has reduced. So the conduction losses will reduce. So the conduction losses will decrease. So now the next question will be, at what value of inductor current should I convert from CCM to DCM? So what is the value of inductor current that for which I will operate from CCM to DCM? So what is the value of IL? So one way I can tell you, let me change the color. So whenever, if you consider any commercial products, so whenever if you consider any commercial project, one of the main motive of theirs will be to have efficiency as high as possible, right? So they will target their product to be as efficient as possible. So you can consider efficiency to be a factor, a deciding factor. So you can draw a plot of efficiency with say I naught, and there exists some point, say this is CCM, say this is CCM, and maybe DCM. So there exists some point up to which DCM will have higher efficiency. So either you can mathematically calculate it and get this particular I value, say I CCM to DCM. So, and they may put some circuitry. So when it detects that this current is lesser than this value, then they will know that they have to operate in DCM, and they will operate in DCM. So these are available in many commercial products. So to improve the light load efficiency, they will not operate in CCM. So the value how they're finding could be one way is the efficiency. So they will always try to target a higher efficiency. So keeping efficiency in mind, they might use some mathematical models or efficiency calculations, and they'll find the current below which it should operate in DCM. And they might also have some circuitry which will detect the current. And whenever it detects that current is lesser than that, then it will trigger, maybe they'll use some trigger, so which will start the DCM operation, so that power losses will be reduced. So this is why we go into DCM to reduce the losses, because there is no need to operate in CCM. So that is one thing. And there are different light load architectures. One is PSM, pulse skipping modulation. Another one is pulse frequency modulation. Another one is peak constant on time peak current based. These things SAR has discussed in the previous course, and PSM has SAR has discussed in the last lecture. So these are some light load architectures. So when a product is considered, any commercial product is considered, they will use multiple these modulation techniques. So at light load, they might be using PSM. At high load, they might be using PWM, or say variable frequency. So they might have some requirements to meet the efficiency. So maybe they accordingly they will decide, because any commercial product will not reveal about their architecture, right? So at what point they are going to PWM or PSM, they will not reveal, because it is a product. So their logic is kept as secret, but this could be one possible way. They might be also considering some other aspects, but efficiency could be one of. Is that clear up to this point?
Yes.
Okay, so now coming to week 6. So in week 6 will be like till week 5. So from week 1 to week 5. So we have discussed about multiple architectures, MATLAB simulations, and different models like continuous time model, discrete time model. And then we have finally discussed the controller design. From week 7 to final week 12, we will learn about the implementation. Say we have designed the controller, how to implement it in the hardware. So first SAR will teach about Verilog, and then SAR will teach about the implementation of digital control using Verilog. But before we go into the actual implementation, so in week 6, okay, let me use another column, maybe green. So in week 6, we will learn about something about say ADC DAC. Why do we need ADC DAC? Because ADC is analog, and it is converting into digital, which is going to FPGA. So what architectures are available in ADC DAC, what we have used in the hardware prototype, and after this, we'll be discussing about something about hardware. Some say inductor, what type of inductors are available, capacitors are available, what type of gate drivers are available. So in our layout, what products we have considered, what type of ADC we have used, why we have used, and is ADC itself is sufficient, or how to choose ADC. So this week 6, and then SAR has ended by showing some demonstration of FPGA. So whatever content or whatever theory we have learned in the upcoming week, and whatever we are going to implement. So before we going into the hardware, so SAR has given some brief description about the architectures and the components that we have used in this hardware prototype, and which we will be using throughout our course. So mainly to start with, I will be discussing about ADC DAC and requirements. So why do we need ADC DAC and different type of ADC architecture? SAR has covered so many architectures, but as I'm only revising, I will not teach all of them. I will only cover which are very crucial. So one is the dual slope ADC, and another is the SAR ADC, and another is the flash ADC. And DAC architectures, SAR has, I think, discussed 2 or 3. I'm only discussing R2 or ladder DAC. And then why current sensing is needed and what type of current sensing techniques are available. So one is non-isolated, isolated. In non-isolated, I have considered these, which we will be discussing, and in isolated, I have considered these 2. And power stage design. So what type of L and C are used, what type of gate drivers are used. So all these things we'll discuss. And then digital control implementation. So I will be showing you the FPGA that we are using, and like what we can do with the FPGA, and then we can solve some problems. So let me get rid of this. There is this bar available, seen on your screen, right? I don't know how to remove this. Okay, let me stop sharing and share it again. Okay. Okay. So first we'll discuss about analog to digital converter, what architectures are available and what we can use. So how to get rid of this. Let us continue. You are able to hear me, right? Hello. Hello. Hello.
Yes, yes,
yes. Okay. So to start with, okay. So to start with, say we have some analog input which is going into our digital control system, which could be FPGA or microcontroller. So this only knows everything in digital. So it is a digital architecture. So it needs digital signals. So whatever analog signals that we are having in our, say, V naught of t, it does not know about V naught of t. So it needs some digital signal in terms of some bits. So we have to convert this V naught of t into the language this FPGA understands. So this V naught of t should be digitized, say n number of bits, say 10 bits or 20 bits. So that's why we need ADC, which will convert our analog input to some digital output, which will be fed into the digital control system. And maybe we will not use DAC in voltage mode control, but in current mode control we need. So whatever I reference of n we have, and this I reference of n is, say, in bits, 10 bits. You cannot compare that with any analog signal, right? Say we have comparator, right? Here we have IL, which is analog, and here we have I reference, which should be compared. So this is analog, because we are using analog comparator. So this is analog comparator. So we are using analog comparator. So input should be analog, as well as this other input should also be analog. So whatever I reference we have, we cannot directly feed it to analog because it is in terms of bits, but we want a signal. So that's why we use digital to analog converter, which will convert the digital signal to analog output, which can be now used to compare with the IL. So that's why, so this ADC and DAC are the interface of the digital control and analog mode. Whatever we are saying, it is analog signals, but the digital controller needs the digital signal. So that's why we use ADC and DAC. So coming to the hardware prototype that we have used, I have also discussed before. So here we have DAC, and here we have ADC. And this is DAC. So the top one is called signal conditioning mode. And there is a board below this, as you can see here, which is the FPGA. I will show the board when we go to the FPGA implementation topic. So whatever signals, so this connector is connecting into the signals between these two boards, right? So whatever analog signals that we are getting, so that will be fed into this ADC as input. And now this ADC output, these are the digital signals going under, which goes into the FPGA, and these signals are coming from the FPGA back to the DAC, and the DAC is giving our analog output. So that is why, that is how here things are getting, the communication is happening. So from our power stage, we are sensing the circuits. So sensed circuits, they are going into ADC. This ADC is sending the data to FPGA. And say if it is voltage mode control, then it will, FPGA will directly give us the gate signals Q. Now the FPGA is giving the gate signals in which board? In this board, right? So we have gate signals coming here. Now this gate signal has to go to this MOSFET. So that's why using these connectors, there are multiple signals that can be transferred from this board to that board to this board. So whatever gate signals that we have that are generated here, let me change the color. So let me put it here. Let me change. So whatever gate signals that are being generated here, those are transferred from there to here using the trace. So this is done in PCB. So these QH or QL are being generated, which are again going into the power stage MOSFET. And if we have, this is for voltage mode control. Now for current mode control, we need DAC as well, right? Because I reference is generated and it should be compared with the IL. So we need DAC as well, which will give us I reference, which is being compared with the comparator. So this is for voltage mode control and this is for current mode control. But the setup is same. Our code in the controller will change, but our entire setup
why
is...
DAC is required only in case of CMC and not in VMC?
Yes. So in the case of voltage mode control, if you consider the architecture, how it will be? We are comparing VCon, right? VCon with ramp voltage. And the output will give reset, and set is FSW. And this is the gate. So when we talk about voltage mode control, we say digital voltage mode control, right? Because everything is digitized. So this Q is coming from the FPGA. So this entire part is there in the FPGA. So this entire part can be implemented in the FPGA. How we can implement that will be discussed in the upcoming weeks, but just for your understanding, this entire thing can be implemented in FPGA. But when we say current mode control, we say mixed signal, right? If you remember, we say mixed signal. Why do we say mixed signal? We say mixed signal because voltage is in the digital domain and current is in the analog domain. So there is some part which is in analog domain, and it should be compared with the analog comparator. So this I reference and this IL, these are in analog domain. Okay, so this is Q. Now I reference is the control voltage, right? Output of the controller. But controller is in digital domain, so it has to be converted into analog domain. So this is my DAC and input is digital. So if I use another color, so the input is in digital domain and the output is in analog domain. Because there is some part in the architecture which is in analog domain, I need my I reference to be in analog domain, but it is generated digitally in the controller, and I have to convert this into analog domain, for which I need a DAC. Whereas in the case of voltage mode control, everything is digitized, so I can implement everything in the FPGA. But if you consider fully digital current mode control, where current mode control, both the loops are in digital, then I don't need a DAC. DAC is not needed, but I need another ADC to sample the IL. So the architecture decides whether we need ADC or DAC, because mixed signal one loop is in analog, so it should be implemented in the analog. Is that clear? Hello.
Yeah.
Okay. So now let us go to ADC. I don't know why this is coming. I don't know how to remove this as well.
Sir,
Yes. Hello.
sir,
Hello.
what you are saying here we are seeing only ADC architectures.
Okay, actually there is a strip that is coming on top of it. So you can read, right? Then if you can read, then we can proceed. I thought you are not able to see. Okay, okay, then fine. Okay, let's continue. So now we are discussing about ADC.
No, we are not seeing any strips.
Okay, okay, fine, fine. So ADC architectures are there. SAR has discussed two ADC architectures. One is the serial, one is the parallel. When we say serial, the data is being fed serially. So the data is fed serially, and here it is done parallelly. So from the name itself, we understood like serial will be slower and parallel will be faster. So this will be slower and this will be faster because it is parallelly done. So today we are considering two architectures. Maybe Sir has discussed more. Here also we'll consider flash ADC, and there is another ADC which is also pipeline. Now it is slower, so it is a bit cheaper because it has its cons, so the price will be cheaper. And here its cost will be more. Because it is faster. So like there will be trade-off for everything. If you want high performance, the cost will increase. If you want it to be cheaper, then you have to adjust with the price. So in serial ADC, first we'll discuss about the dual slope, then successive approximation resistor ADC, and then flash ADC. So coming to the dual slope ADC. So forget about the circuit or what exactly is happening is there are two voltages. Our V in star should be converted into digital domain. So we are considering another known reference. So this V reference is known. So we are using this V reference node to find this value. So how are we doing that? So the first thing is this is an integrator circuit. You might know. If you find the equivalent output voltage by input voltage, it will be 1 by S, some K by S into the input. So it is an integrator circuit. So basically what we are doing is with this wheel, we are integrating it, right? And this is an inverting amplifier. So because this is V in star and this is inverted, so it will be integrated in the negative direction, which is being shown here. And RC constant is coming from this RC. So, so it is being integrated in the negative direction. Now, in the first case, we are fixing the time. The time is N reference into T. So N reference is also known. N reference is known. V reference is known. V in star, that is the input voltage. So using this V in star voltage, I am using this circuit to integrate. So this is the VC, right? So VC output, I am integrating it for fixed amount of time. And after the time has ended, now I'll turn this switch on. So now my minus V reference is connected. Why minus reference is connected? Because this is an inverting amplifier. I want it to increase. So the input should be negative as there is an inverting sign here. I'm using minus I reference, which is a known. So minus V reference is also known. So using this known voltage, I am integrating till what point? Until it crosses the zero. So this is zero crossing. So zero crossing. So how do I know the zero crossing? I am comparing it with an ground. So whenever this minus crosses this plus, there will be a trigger coming over here, right? So there is a control voltage. So this control voltage is what? After this fixed amount of time, I am having a rising edge. So there is a rising edge here, and there is a rising edge here, and the clock is also having a rising edge here. So the clock is also having a rising edge. So that's how they are using this. And now when they are counting, when are they counting? So whenever this fixed amount of time is started, or ended, whenever this fixed amount of time is ended, then they are starting the counter. And whenever it is like crossing the 0, then they are stopping. So whenever this 0 is crossing, they're sending a signal so that the digital counter is stopped. So they're counting in this duration. Now, I know the slope, and like V in star by RC is the slope, and this is fixed time. So can I calculate V naught? V naught is the height. So how do I calculate V naught? This slope into the base, right? So V naught is what? V naught is only consider the magnitude. I don't want sign. So V in star by RC into fixed amount of time, which is N reference T. Now here the time is unknown. So NT. Again, this is the height of this triangle with the slope V reference by RC, and time period say NT. I want to find N. So this is equals to V reference by RC into NT. Now let me change it to other color. So TT get cancelled, RC get cancelled. N is my unknown. So N is what? N is nothing but V in star by V reference into N reference. So this is my output. Here, this N will be coming in terms of bits. So my N is nothing but N reference into V in star by V reference. So why is it called a dual slope? So there are two slopes here and here, because of which it is called a dual slope. You need not have to understand it very thoroughly, because we just wanted to make you understand what type of architectures are there. So just to summarize, we are integrating it in the negative direction using input for fixed amount of time. And after that fixed amount of time is over, then I am integrating in the positive direction using fixed voltage for unknown time. And I am calculating this unknown time using this, they have the same vertical height. So I'm equating both the equations. Now I'm getting N. So for given V in star, for fixed N reference and V reference, I'm getting N, which gives me the digital equivalent of V in star. This is one architecture, and the other one is successive approximation resistor ADC. So in this ADC, what happens is, say there is N bit resistor, say N bit resistor. So I will say Bn minus 1, Bn minus 2, up to so on B1 and B0. So what they'll do is they'll start from MSB and then they'll go to B0. So first they will have to find Bn minus 1, right? So this is my V input. So V input will be compared with the half of that fixed difference. So half of V output. So this is my half, right? So this is my 4 by 8. So first they will compare it with V reference by 2. They'll compare V naught with V reference by 2, whether V naught is greater than V reference by 2 or V naught is less than V reference by 2. So this is the comparator that they are comparing. So if my V naught is greater than V reference by 2, then my first bit will be set 1. So the basic logic is this. So every time they'll compare V out with V reference. Sorry, it is not. So they'll compare this V in with the V out. Let me erase this. So V in is fixed. Every time they compare V in with V out. So V out they'll be increasing in the binary fashion. So they'll start with 0.5 V reference is equals to V out. Now they'll compare this with the V in. If my V in is more than this, then they'll compare with 0.75. If my V in is more than this, then they'll compare with 0.8125 or something. So they're incrementing in terms of half plus 1 by 2 square plus 1 by 2 cube up to so on. So they're incrementing in this way. So first what happens? So they'll check if my V in is greater than V out. If this is happened, then that bit is set 1. If my V in is less than V out, then that bit is set to 0. Say this is my V in, which is slightly greater than 5 by 8. So first V in is compared with, so can anyone tell me what is the value of 5 by 8? It is around how much? 0.6, right?
It's on 2.
6. Now V in is compared with the 0.5 V reference. So V in is more than that, right? So my first MSB is set to 1. Now V in is compared with what? 0.5 plus 0.25. Again, there is less than a minute. So if this meeting ends, please join it again, then we can continue our discussion. Now it is compared with 0.5 plus 0.25, which is 0.75. My V in is less than 0.75. So this bit is set to 0. And again, my this is my last bit. So now they'll compare with 0.5 plus 0.25 plus 0.125. And then accordingly, the last bit will be set. So this is how successive approximation register ADC will work. So they are doing it binary. So if my input is less than 0.5, then they'll compare with the 0.25. If my input is less than 0.25, then they'll compare it with 0.125. So they're just doing the binary such kind of thing. So they'll start with this. It will break into 2. Now each will be break into 2, and then each will be break into 2. So they'll compare it, and then they're shifting it. So it starts. So they are using this n-bit DAC. So accordingly, so the input to this DAC is V reference. So they make the arrangement in such a way that this will start with V reference by 2. And then depending upon the output, either it will increase plus V reference by 4 or decrease minus V reference by 4. And say we are starting with V reference by 2, right? So depending upon my output that is being fed here, so it will either increment plus V reference by 4, or it will decrease minus V reference by 4. So now we are at this point, right? Okay, let me change the color. So the hardware is made in such a way, so either you will go here or you will go here. Say I have gone here. Now either V reference by 8 should be added or it should be subtracted. So either you should go here or you should go here. Say I am now here. Now either you add V reference by 16 or you subtract V reference by 16. So this circuit is made in such a way that this DAC will generate that V out, which will be compared. So it is like a binary tree. So we start with the half of the value, and we go into the two sub branches, and it will increase exponentially. Understood, Banerjee? Yes. So this is very widely used. It has a very high performance and high sampling rate, but not compared to the parallel architecture, and the power is also low. As you can see, we are doing it serially, bit by bit. We are comparing it, and if the number of bits increases, so number of such modules will also increase, which will increase the time. Now coming to flash ADC. In flash ADC, see here we are using how many comparators? We are using one comparator, right? One comparator, and we are doing it binary. Say in the case of flash ADC, they have many comparators. So how many comparators they have? 2 to the power n comparators. So if it is n bit, then the number of comparators, like they need from 1 to 2 to the power n minus 1. So they will need 2 to the power n minus 1 such outputs of these comparators. So for this 2 to the power n, like what happens is we need 2 to the power n levels. So for that we need 2 to the power n resistors. So we are increasing the comparator. So like there will be, say, V reference. If there are only 2 resistors, so we'll have V reference by 2. Now, if we have 2 to the power n resistors, we'll have V reference 2 to the power n, right? So we are creating so many levels, and all of the levels are being compared with the multiple comparators, which is being fed to this priority encoder, which will generate me my output n bits. So I am increasing the number of comparators as well as resistors, which will definitely increase my cost as well as area. So there are so
why
many.
is the power n, sir? Like if we are increasing the number of resistors, like the precision increases?
Yes. See, here we are doing exponential increment, right? So The output is how many bits? Here output is how many bits? Here 1 bit, here 1 bit, here 1 bit, right? Isn't it? 3 bits, right?
Yes, sir.
But how many levels we have? 1, 2, 3, 4, 5, 6, 7, 8. Because 2 cube is 8. So we need such 8 levels of such values, right? We can generate 8 such values using these 3 bits. Now, instead of going binary way, they are generating these 8 values using the resistor divider. So using this resistor, they are generating that V out by V reference values, which is 2 to the power n. And then they are directly comparing using the comparator to get the bits. Now they have to decode it to n bit.
Okay.
Yes. So this will significantly increase the cost as well as area. So it will be very high cost and also more area. And if n is increasing, then the cost will increase exponentially because it is proportional to 2 to the power n. So the component requirement also increases exponentially, and this is the drawback. Like it is super fast, but the number of components as well as the cost will be very high. And depending upon the priority encoder, we'll get the output. So this is working of priority encoder, but I'm not going into the details of this. This is just to for your understanding. Like this is not for exam or test your understanding, but if you want to go through, then you can go through. So this is the working of the priority encoder. Now coming to digital to analog converter. Now we have discussed analog to digital. So again, we need digital to analog converter. Now we will be discussing only one R to R ladder. So requirement we have already discussed because it is needed in current mode control, and voltage mode control DAC is not needed. Okay, so coming to the DAC architectures, here also we have serial architecture as well as parallel architecture. Serial is charge redistribution DAC, which is not discussed in this course, and you need not know. But if you are interested, you can search in some online material and go through. And SAR has, I think, discussed MOSFET current sinking, but I'll be discussing only R2R ladder just to give some information to you. So in R2R ladder, what they will do is they have this R2R ladder. Why we are calling it is R2R ladder? So in the serial we have R, and in parallel we have 2R. And in the last branch, what do we have? Here we have R, here we have 2R. So these are all grounded. And finally we have 2R here. Right. So 2R parallel will be what? R, right? Isn't it? 2R parallel. What is the equivalent resistor? So if I draw the equivalent resistor, now this will become R, which is in series with R. So this entire thing will become 2R, which is again series with 2R. So it becomes R, again in series with this R. So it becomes 2R. So finally what we will get? We will get R here and 2R here as well as 2R here. This is the final equivalent circuit. Now if I reduce it even further, we will have R and R over here. Yeah.
Please repeat this one.
Okay. So we have 2R and 2R over here, right? So they are in parallel. If they are in parallel, the equivalent resistance will be R. So these two are in parallel. The equivalent resistance will be R, which will come in series with this. So in the horizontal, we have resistor small r, and in the vertical, we have 2R. So when I am paralleling these 2R with 2R, I'll get a single R. Now this R is in series with this R, which becomes 2R. And then there is another branch here, which is also 2R. So what it happens is, basically it is vertically it is becoming 2R, and if I reduce one step, then it again becomes R2R. That's why we are calling it R2R ladder. So even if you reduce it, finally it becomes R, and 2R, there will be two 2Rs in parallel. So this is the final circuit. So this is my V reference and this is my ground. So this is the complete reduction of this circuit. So now what is the current? V reference by 2R. Current in this, right? Understood until this point?
Yes.
So the I out, the current into the op-amp is 2R.
Current
V
in this
reference by
branch,
2R.
in this branch, I is V reference by 2R. I is V reference by 2R. Forget about the op-amp, we have not gone till this part. So in this I branch, we have, sorry, this R is not there. So we'll get V reference by R. So the current here is V reference by R. Now this V reference by R is being divided in 2R as well as 2R. Right. So I naught will be V reference by 2R. And in this will be V reference by 2R. So maybe there is space constraint here. Let me go back to this part. So I can use this space. So the circuit is like this. 2R, R, 2R. Say I have reduced the number of bits. 2R. So this is the overall circuit. Think this is the overall circuit. Because this 2R is coming because there is this 2R. So here one 2R is there, here another 2R is there. So I have reduced the number of bits and this is my final circuit. Now if I combine these two, what will be my circuit? R, R, right? If I combine these two, there will be 2R parallel with this 2R and my equivalent circuit will be R. So this is my equivalent circuit with input of V reference and current will be V reference by R, right? So that is the current coming here. Understood until this point?
Yes.
Yes. Now, if I combine these two, it will be 2R. So 2R parallel with 2R. So the current will be divided equally, right? So in this branch, V reference by 2R. And in this branch, V reference by 2R. Now this R has come because there are two 2Rs in parallel. So in this branch, my current is V reference by 2R. But there are again two 2Rs. So again, it will be divided into V reference by 4R, V reference by 4R.
4R.
So V reference by 2 square R I'll write. And here I'll write V reference by 2 square R. And from here I got it is V reference by 2R. So the circuit is in such a way that if you consider this 2R currents, they will decrease exponentially. So 2R, 2 square R. Again, this 2R will be like, if you increase it, then if you come back here, at any point, if you consider there is one 2R in parallel with the 2R. So this will decrease exponentially. So our I naught is what? Our I naught is V reference by 2R and I1 is V reference by 2 square R. So this is a generalized equation. So if you substitute in that, we'll get all the currents. Now coming back to op-amp. So if the switch is on, then this will be connected. This will be connected. Say all are on. This will be connected and this will be connected. So all these currents will be added up. And all these currents will be going in this way. So if I calculate the summation of currents, say I out will be summation of all these currents, right? So V reference by R, if I take common, it will be, say, this is B0, this is B1, this is B2. So whenever switch becomes 1, then only current will flow. So if B0 is 1, then only the current will flow. So B0 by 2 plus B1 by 2 square plus up to so on plus Bn minus 1 by so if it is 1 here, it will be 2 to the power n. Now this current is flowing into KR. So V out is what? My V out will be KR into this current. So K into V reference into B0 by 2 plus B1 by 2 square plus up to so on plus B to the power n minus 1 by 2 to the power n. But this is an inverting amplifier, so there will be a minus. So that is how we are getting this equation. Because if B0 is 0, if B0 is 0, it is connected in this path. So the current will not flow. So if B0 is 0, the current will not be coming in I0. So the circuit is made in such a way that if it is connected, current will flow, the summation of the currents will flow through this. That's why, and B naught is the MSB because it is half, so it is MSB, and this is 1 by 2 to the power n, so this is LSB. So depending upon which bit is on, the current, that particular current will be added up and it is fed to a resistor so that we will get equivalent voltage. Now there is a minus sign. Maybe if you want a plus sign, then you can put another unity gain inverter so that it becomes plus. So they might
Actually, B naught.
Yeah, sorry.
Actually, B naught, B1 are bits, right?
So this is B naught. B naught is related to S naught. So if S naught is on, then B naught is equals to 1. If S naught is off, then B naught is 0. Similarly for all the switches. So when the switch is on, it is this. So this is on. And this is off. So if the switch is on, it is connected through the op amp. If the switch is off, it is directly going to the ground. So whenever it is on, the current will be added up and it is passing through op amp. Whenever it is off, that current is not passing through op amp and it will directly go to the ground. So we want those currents to be added up whose bits are 1, because that bit will be giving my equivalent V naught, right? So accordingly, we are doing it. Is this clear until this point?
Yes.
Yes. Okay. So we have discussed about ADC DAC, and one thing I have not discussed is the pipeline ADC. So I'll just give a brief discussion about pipeline ADC. So if you consider serial ADC, all the bits are coming in serial, so which will increase the time. So the time to convert will increase. But if you consider flash ADC, the cost is more. There are so many components, exponentially it is increasing, so cost will be increasing. So pipeline ADC is a combination of these two, we can say. So which color I have not used, maybe yellow. So pipeline yellow will be close. So pipeline ADC is a combination of these two. So SAR has discussed. I'm not going in detail because it is somewhat high beyond this course, and we will not be again asking questions on your understanding of pipeline ADC. But the other ADC what I have discussed today, those are mandatory. So in pipeline ADC, they'll consider 2 flash ADCs here and here, and they'll convert this in serial. Say here we'll have n by 2 bits, here we'll have n by 2 bits. Now in the case of flash ADC, how many resistors we need? 2 to the power n resistors, 2 to the power n minus 1 comparators. Here how many you will need? 2 to the power n by 2, 2 to the power n by 2 minus 1. And here again 2 to the power n by 2, 2 to the power n by 2 minus 1. So we are in serial ADC, there are so many, say for 3 bits or say n bits, we have n such serially connected. In the case of here, we have only 2 such serial. So we are taking the advantage of serial ADC where the cost is less, and we are taking the advantage of flash ADC where the time is less, conversion time, and we are combining both of them. So we'll get advantages of this as well as advantage of this, and we will not have many disadvantages because it is 2 to the power n, here 2 to the power n by 2. So if it is 6 bit, in flash ADC, we will be needing 2 to the power 6, which is 64. But in the case of flash ADC, requirement will be less. If it is not n by 2, then accordingly it will be reduced. So that's why we are going for pipeline ADC. And I'm not discussing because you don't have to learn too much of the architecture of pipeline ADC. So just as a discussion. So now we'll go into current sensors.
Hello.
Yes, yes.
Yeah, actually, in a course, ADC driver is there, ADC DAC driver.
Yes, yes.
Why they are using? What is the purpose?
Yes, yes. I'll come to that point in the upcoming slides. I have put ADC driver as well as DAC driver. Okay. So why do I need current sensing? Because in the case of current mode control, I need current information, right? So I have to compare my inductor current with some I reference. And this should be some equivalent voltage. So I have to sense my inductor current and it should be fed to my comparator so that I can compare and I'll get my reset signal. So for current mode control, we need this equivalent inductor current as a voltage form, and that will be compared with the I reference. So for that purpose, we need current sensing. And there are so many advantages of sensing the current because we can put a peak limit. Say each hardware component has its own limitation that say its rated current is limited to 10 amperes and you don't want the current inductor current to cross 10 amperes. So we can put a peak limit so that whenever it hits the limit, maybe we can turn off. So we can we should know the inductor current information, right? So whenever it is increasing, I can put a limitation so that after that I can turn it off. So for protection purpose also, we need inductor current information. Say if the current has crossed its maximum limit, I want to shut down the circuit for protection purpose because I don't want the components to be damaged. Then I can put a limit so that whenever it touches the limit, I'll shut down the complete system to protect the components by not allowing higher current. So for that protection purpose and in current mode control, and we have discussed trajectory based in last week, we have discussed trajectory based control where we are shaping the inductor current. So we need the inductor current information as well. So in advanced control architectures also, we might be using inductor current. So for all those purposes, we need the inductor current sensing. And we need high frequency because we are operating at high frequency. We need the ripple information because when we are comparing, we need the ripple information as well. So we need the ripple information, and there are many ways. So one is the non-isolated way, and the other one is the isolated way. So coming to non-isolated way. So there is something called inductor DCR sensing, and we know that every inductor. Let me change the color. So every inductor has its own DCR, L, R. So we will be tapping the voltage across this, and why we are putting R and C, I'll come to that point. So this RL will be in say milliohms and this resistor will be much higher. So whatever current IL, we can assume that this current is very, very less. So we can ignore that it is almost very negligible current is going through this. We can assume that the entire current is flowing through this because Rx is much, much higher. So current will choose the least resistance path. So the assumption is that IL is completely passing through this, and also in the circuit Rx will be much higher and all the entire current will pass through this. So if the entire current is passing through this, what is this voltage? Say this entire voltage is some V dash. My V dash is IL into SL plus RL, right? So now this same voltage will appear across this R and C. And if I want to find VCX, what will be my VCX? 1 by SCX by RX plus 1 by SCX into V dash. V dash is IL into SL plus RL. Now, if you take division, it will be 1 by 1 plus S RX CX. Take RL common here. So it will be SL by RL plus 1 into IL RL. This is VCX. Okay. So now one thing I would like to do, I would like to cancel this term. So I want this and this to be cancelled so that my VCX will be how much? IL into RL. So I am getting my voltage as a scalar multiple of inductor current, which is my aim, my objective. So this will happen when these two get cancelled. So what is the condition? L by RL is equals to RX CX. So this is my condition. I have to choose Rx and Cx in such a way that it is equivalent to L by RL. Say you have selected the inductance. You can go to that inductor datasheet and you can get some approximated value of this DCR. So they'll be mentioning what is the DCR. So you know L and RL. And from there, you can get RC expression. You will get Rx into Cx is equals to some value. So you have to choose Rx and Cx in such a way that this product will be equivalent to that value. In such case, my IL will be equal to RL. So L by RL should be equal to Rx Cx. Now I have done, say my inductor current is IL. My RL is how much? Very less, right? Milliohm. So I'll consider 1 milliohm. Say my inductor current is 10 amperes or 1 ampere, say 1 ampere. Then my VCX is how much? 1 millivolt, which is very less. It is almost, it will be detected as noise, but I want it to be somewhat higher. So I have to increase the gain. So for increasing the gain, we are using differential amplifier. Why are we using differential amplifier? Because this is some floating voltage, not ground. This is also some floating voltage, not ground. So there are two floating voltages which are not ground. So for that reason, I am using differential amplifier. Say if you consider a non-inverting amplifier, here you will have voltage. This is single-ended, right?
When the term floating will be used?
When that floating, see, I mean to say it is not grounded. See, if I want to use a non-inverting amplifier, its input is single input, right? So it is called single-ended, and the output is also single-ended. But I am taking two voltages, and one of them is non-zero. So I am taking the differential voltage, right? Say VC, this point is V1, and this point is V2. I want my gain output V sense to be some K into V1 minus V2. So this is a difference, right? Which is equal to VCX and non-zero. So I want the differential voltage to be gained. That's why I'm using differential amplifier. If one of them is grounded, then I can take a single-ended amplifier. And the other, say, I'll give the input with respect to ground, and my output will also be with respect to ground. Because one terminal is grounded here. But in the case of this sensing, both the terminals are non-zero terminals. So I should take the differential voltage and then increase the gain. That's why I'm using differential amplifier. And you know the gain of this differential amplifier is how much? RF by RA. So this you have already learned. So I'm not going into the derivation of that. So now my Vsense is how much? So I have discussed VCX is IL into RL. And now I have considered a gain of RF by RA. So the overall final expression will be my V sense is equals to IL into RL. This is the VCX multiplied by a gain RF by RA. So I am sensing using inductor DCR sensing, but then I have realized the gain is very less. So I am increasing the gain with RF by RA. So accordingly, I'll choose RF RA. Say if I want gain 10, I'll choose maybe 10 kilo, 1 kilo, or 500 ohm, 5 kilo. So that is your choice, what resistors or what gain you want. So that is all about the inductor DCR sensing. So there is this data sheet which we can go through to get the details. Yes.
Hello.
Yes.
DCR stands for?
Sorry, DCR stands for
DC.
direct current resistance. So it is in series with L, and here we have ESR, equivalent series resistance. Yes, someone was asking.
Hello.
Yes.
Yeah, actually, in reference schematic, what SAR has taught in this lecture,
in
there the current sensing reference schematic, but reference schematic is there. Schematic diagram.
Yes.
Yeah, for that, for sensing, current sensing,
yes,
they are using two differential amplifiers for sensing the current, and they are and they are combining, and they are using one amplifier in output.
They are using two differential amplifiers, and they are like
then they are single-ended.
That circuit, is this the circuit or some other circuit?
Yeah, exactly.
So this is one differential.
Some other circuit.
Okay, but as far as I have seen, SAR told they are using this sensing. So I think they'll be using one differential amplifier, or maybe they have.
Yeah, actually.
Continue.
Actually, that for resistance, the RSH is there. No, they are giving L and S some notation.
Okay.
For one point, they are using this differential amplifier. That for other point in RSH, other point is there, other lead is there for resistance. For other lead, they are using another differential amplifier.
Okay.
And they are combining both. For let's say for one lead of resistance is P and one lead of resistance is L. They are using L for L. They are using one amplifier, and for P also they are using another amplifier.
Okay.
Yeah, I will share you on that image if I found.
Okay. I'm not sure about that schematic. So, like as far as I know, they have used differential amplifier, but I'll check and I'll get back to you.
Yeah.
I'll keep that in mind.
Sir,
Yeah.
sir, in the schematic, this IL,
IL.
this IL, this IL is the, is it the average current, sir?
Yes, we are considering IL to be average current, but it also has ripple information. But that's why, like, you can say it instantaneous current, not average current, because we are getting the ripple information as well. Like with the ripple. Not
So
the
the
average.
sense voltage will also be
Yes,
changing.
the sensed voltage also will have ripple, and we want the sensed voltage to have ripple because this we will be comparing with the comparator. We want the ripple information, right? That's why we are using this thing. Understood?
Sir, but we are comparing a VCon. This is actually VCon.
No, this is IL.
V-sense. Okay.
IL. So if you consider this comparator, so we are comparing IL with I reference, right? So this IL is this V-sense. Not exactly IL, some gain into IL. So this gain into IL is this V-sense, because now it is equivalent voltage, though it has current information, but it is in terms of voltage, right? So K into IL volts, and I reference is coming from my DAC output. The input is coming from the FPGA. Is that clear? Okay. So this is the inductor sensing, and coming to the current sense resistor. So one thing they can also do is they'll connect a some resistance RS in series with the inductance, and they will tap the voltage across this VRSH. So you may think this is lossy. Yes, this is lossy, but this RSH will be in terms of like in the range of 1 milliohm to 1.5 milliohm. So it will be very less. So the loss, there will be some loss, but the loss, it will not be that much huge. So now again, say this voltage is how much? My VSH, say I'm naming this as VSH. VSH is IL into RSH. And RSH is in 1 milliohm, so the gain will be very, very less. I want to increase the gain. So again, I'm using the differential amplifier, VSense, which is RF by RI into IL into RSH. So this is my final VSH. Now, you may all know that the op-amp will have a bandwidth, right? And there is something called gain bandwidth product, which is unity. So if you are using op-amp, gain bandwidth should be unity. If you increase the gain, then the bandwidth will decrease, the actual bandwidth. Say the op-amp has a bandwidth given. Say it is a 100 megahertz or 200 megahertz bandwidth op-amp. That bandwidth is when you operate it in unity gain. But now we are operating it at a gain of what? We are operating it at a gain of RF by RI. So now the bandwidth will be reduced. So bandwidth will be reduced by this gain amount, because bandwidth into gain is equals to 1. So at unity gain, the bandwidth is bandwidth given. I'm naming it as bandwidth given. Now, if we increase the gain, then the bandwidth will reduce. So the bandwidth actual will be bandwidth given by bandwidth gain. And there is this thumb rule that if you want to say a signal has some frequency F. Now the inductor ripple has this frequency FSW. If you want to retain this information, then the op-amp bandwidth should be at least 10 times more than the switching frequency. So this is a thumb rule. So that bandwidth should be at least 10 times more than the switching frequency. So this bandwidth actual should be more than 10 times of switching frequency. Now my bandwidth actually is bandwidth given by gain. So my given bandwidth at unity gain should be greater than or equal to 10 times switching frequency into gain. So this is the consideration I should keep in my mind when I'm selecting the op-amp. So if you are operating at high switching frequency, then the gain of the bandwidth should be high. Depending upon the bandwidth of the op-amp should be high, depending upon the gain. So this we should keep in mind. If we do not follow, what will happen? You will not get the exact information of the ripple. So it will be kind of filtered out. So we might not get the exact information. So the ripple information might be lost. So it is like filtering out, right? So the higher order frequency components might be filtered out, and offset with low frequency components will be present. So we will not get the exact peak. So if you want that peak, and which we actually want, we should keep this in mind, in our mind, and we should consider or take the op-amp which will hold this. And my vsense is RF by RI into IL into RSH. So this is the consideration. But so this is when we consider a equal or series RSH connected in series with the inductance. So we got the final expression. But so again, this is in this analog devices datasheet. If you want to go through, the link is embedded in this text, so you can click it and you can go through that. What actually happens is, yeah.
Sir, in the last case, what is the major difference between the RL and this shunt current sense resistor?
Yes. So here inductor has this RL.
Mm-hmm.
So inductor has RL, and previously I was tapping between this point and this point, right? So I'm tapping between this point and this point. Now I am connecting another shunt resistor, RSH, and I am tapping RSH, and I am tapping this point. So RL is with the inductor. So in the previous case, we are tapping the inductor points. Now I'm tapping resistor points. Now what happens is every resistor. Yes. Yeah. So the DCR is present here.
Yeah. Sir, since we can't separate this, there.
Yeah.
Then.
So this is not DCR. This is additional resistance that we are adding. This is not DCR. DCR is here. This is not DCR. This is not.
Yeah, that
DCR.
is okay, sir. But this DCR we can't separate more, right?
Yeah, no, we cannot separate, right? Like it comes with the inductor. Say the inductor has two terminals, right? So within the two terminals only, in between we have this RDCR. So when we are saying that we are tapping these 2 points, these two are the inductor tapping points. So within the inductor only we have this equivalent resistance coming. So this is one way where we tap the voltage across the inductor, and this is the other way where we are
actually we are considering impedance there in the last case.
This case.
No, sir. This is we are considering across RSH. This is
yes.
okay. In the previous case, we are tapping across impedance.
Yes, L plus RL equivalent. Yes.
Inductive impedance.
Yes.
Sir, actually the other doubt is, sir, in the next case, we said the gain bandwidth should be unity. Suppose if we consider a low pass filter magnitude plot, a low pass filter magnitude plot. So at that time, when we increase the gain, the bandwidth also will increase, sir.
No,
for a low pass.
See, what they gain bandwidth meaning is, say, for every op-amp, it has a gain, right? Now, if you increase the gain, then what happens is the bandwidth equivalent effective bandwidth of the op-amp will be reduced. So it comes from the gain bandwidth equal to 1, which is for a first. Again, there is less than a minute. So if this meeting ends, please join again. So this is for first order filter.
Sir, if I increase the gain, the magnitude plot will go up, right?
Yes, and the effective bandwidth, I'm not talking about the bandwidth of the system, the bandwidth of the op-amp. The functionality
Okay.
of the op-amp is in such a way, it is like a first order filter. And for first order filter, we know that gain bandwidth plot is unity. So for this, if I increase gain, the bandwidth of the op-amp will reduce. I'm not talking about the bandwidth of the this Bode plot. I'm talking about the bandwidth, effective bandwidth of the op-amp itself. So this is coming from the op-amp functionality.
This is the actual bandwidth.
Yes.
That what should be great.
Can you see my screen?
Yes, sir.
Okay. So this is coming from the op-amp. So like we cannot continuously increase the gain and expect this output will also be having that ripple information. So this is the functionality of that first order filter. So we cannot operate at the higher bandwidth for higher gain.
Okay.
Now what happens is, say even if we are considering RSH, we are thinking that it is purely resistance, but it will also have some inductance, say LSH. Now, when there is a resistance and inductance in series, we have got from the DCR that in order to cancel the pole with the zero, we have considered one equivalent resistance and equivalent capacitance in series, such that this equivalent entire circuit will be in such a way that pole will be cancelled with the zero. So whatever R shunt resistance we have considered, it will also have L shunt resistance. So I am considering a resistor and a capacitor, and this is RF1 and say RF, and this is C. Now again L by R, LSH by RSH should be RF into C, right? Let me go back to check. So it is R into C. So this will be RF into C. So using this equation, you will get RF and C. They have divided RF into RF1 and RF2 so that it will look identical. So whatever voltage we are tapping it, so if there is any drop across this resistance here, the same amount of drop will be coming here. So for that purpose, they have put two resistors, but you can put a single resistance. Now they are again tapping this voltage and sending it to a differential amplifier, which or the differential amplifier gain is RG by R1. So my VCOM will be IL into RSH. We have discussed, and this will cancel this equation will make sure my pole is cancelled with the zero, and my VCOM is this, and gain of the op-amp is RG by R1. So if I consider this to be my V output, so my V output will be VCOM into the gain, so RG by R1 into IL into RSH. So this is how we'll be doing, and this is what has been done in the hardware as well. But as you have mentioned, they are using two differential amplifiers. I will check and I'll get back to you. Yeah.
Sir, could you please repeat this point? Like you are using that C and L combination. It is actually discussed in the previous slides.
Yes.
You are
yes.
using the same concept here.
Yes.
So could you please explain that starting point?
So I am telling here inductance has resistance in series, because of which we are getting a zero. But in order to cancel this zero, or in order to compensate this, we have connected a RC circuit such that the pole is cancelling the zero, and my effective voltage is just a scalar multiple of inductor current, not any S term is coming in this final expression, right? So my aim is this. But here, when we have considered R shunt, we are thinking that it is only resistance and it will be a scalar product, but it is not like that. If you go into any sense resistor datasheet, they will mention that it has some inductance, though it might be small inductance, but there is inductance. So because of which my voltage will be SL plus R into IL. So I have to compensate this. I have to cancel this 0, for which I am using the same concept that we have discussed before, which is connecting a RC circuit in series. Now the entire expression will be same, right? Only here I instead of R DCR, I have R shunt. Instead of L, I have L shunt, not shunt, L the sense resistor. And instead of RX, CX, I have RF into C. So the entire expression remains same. Now I will choose RF and C in such a way that this equation will be holding good. And then I have again used the same op-amp, the differential amplifier, so that I will get this much gain. Now you have asked me that why this will be RSH into I measurement. So when you calculate RF, it will be in terms of say tens of ohms, say 10 ohm, or say let us say 20 ohm or 30 ohm, something like that. And my R shunt is around 1 milliohm. So if I connect 1 milliohm and 20 ohm, so if there is a current flowing, you can like you know that the current will be around maybe say 99% flowing through this, and say 1% or less than 1% flowing through this. So if I want to find the voltage, my voltage will be, say this is IL. My voltage is nearly equal to IL into 1 milliohm, which is RSH. So my voltage will be RSH into I measure, because the current that is flowing is almost negligible, tending to 0, because it is very high resistance path compared to this. But I want to tap the voltage, which will be coming across the capacitor. So my work is done, and that's why I'm going through this method. I am connecting RC circuit in order to compensate that pole. So in order to compensate that 0 with a pole, so that my final VCOM is just a scalar multiple of the current. Understood, Banerjee?
Yes, sir. Yes, sir. You are saying that RF1 is very much greater than the RSH, right?
Yes, yes.
Okay, sir. Okay. Okay, sir. Got it. Thank you.
Yeah. So even if you go in the hardware and if you calculate, you can consider any sense resistor, you can calculate R and C. The R will be much higher than R shunt, and it will be around 20 ohm to 30 ohm. So it will be much higher. So the current is, you can consider to be 0, because it is less than 1%. So that is why the voltage will be scalar product of RSH. And because the RSH is very small, the gain is not sufficient, for which we have to increase the gain, and we are using differential amplifier. So this is the final expression of this circuit, and this is also present in this datasheet. If time permits, I can open this datasheet and go through, but this we can do at the end as well. So first let me complete what are concepts I'm planning to complete today. So this we are connecting the resistance when we want both high side as well as low side information, but we can put the resistor in the high side switch in series with the high side switch. So in that case, you will get the this information only. So we are getting the peak information. People put this because for protection. So they put a resistor here and they sense the current. So if the current is crossing limit, then they will take the necessary measures like turning off or shutting down the circuit or so. So for protection purpose, they use this because they'll have the peak information, right? So that is why they are using high side sensing for protection. Also, it is not connected to ground, so there is no ground disturbance. So whenever there is some switching happening, so ground will have some certain kind of disturbance, so which will not be reflected here. But again, the issue is it is difficult to sense because there are two floating voltages. You have to use a differential amplifier, which is somewhat costly, I would say, with a normal amplifier, because it is a specific amplifier. So it would be difficult to sense compared to the low side sensing. And as we get the peak information, we can use peak current mode control. And as I have mentioned, we have to go for differential amplifier. That's why we need differential measurement. And let us see if time permits, then I'll open this datasheet and I can check. Now coming to low side sensing, they put sense register here. So the inductor current waveform is like this, and they are sensing during the off time. So they'll have the value information, And now it cannot be used for protection because we will not get the peak information as accurate as the high side sensing. So people generally don't use this for protection. Only high side sensing will be used for protection. Now, low side sensing has valley information, so we can go for valley current mode control, but there is a ground. So as I told, there will be some disturbance, some kind of noise at the ground, which will be again reflected in our sensing as well. So that will be there. So ground disturbance will be coming in our thing. As it is one is grounded, I can use a non-inverting amplifier and I can directly amplify this voltage. This voltage. I can directly amplify this voltage. So it is comparatively simple because I don't need any differential amplifier. And as I have discussed, it has valley information, so I can use valley current mode control. And this is a single-handed measurement because one terminal is grounded. So I can use single-handed measurement, which is somewhat simple compared to the differential measurement. And if you want to do peak current mode control with this, you have to sense the valley and you have to go for digital current mode control. And you have to emulate the current inside it. But again, this I'm just giving information, but this is somewhat higher level topic. So just to give you some information. So majority of the products use this low side sensing. So high side sensing also they'll use for protection, but for control they use low side sensing, and accordingly they choose their control architectures and everything. Again, this is present in this data sheet. Yes, sorry.
Sir, you were saying something about this digital CMC.
Yeah. So what happens is we have discussed about digital current mode control, right? So in digital current mode control, I have discussed that we have to sample the inductor current and we have to emulate it, right?
Okay.
So
Yes.
if my inductor current is like this, what I can do is, if I still want to do peak current mode control, I'll take a sample here. And if you remember, we use that sample to emulate the current. So it has, to emulate the current. So it has MC. So using this sample, we are emulating it. Now we are emulating it. Now I can do peak current mode control and then I can turn it off. So if you still want to do peak current mode control with this valley information, we will take a sample and then emulate it. But this has its again pros and cons because we have discussed some stability issues will be there. But this is just a provision. You can go for digital current mode control and you can do peak current mode control. But then you have to emulate the inductor current. So this is the hardware prototype that SAR has used, and SAR has already shown in his lectures as well. So the violet waveform is the IL sensed. And this is using the probe. So say this is the switch node. And this is the inductor. They put a wire over here and they'll use a probe. They'll connect a probe across here and it will show the inductor current waveform. So this we are not sensing. This is just a visualization, and this is the actual signal that we are generating using that. What is the name of that? Series resistance and differential amplifier. And this is the IL. This is used using probe. So there, as you can see, there is some noise at the switching, but SAR has overlapped and they are perfectly overlapping. We are getting the entire ripple information. If you see the scale of this is 100 millivolts. Yeah.
Sir, here one is censored directly and the other is like from resistor they calculated, right?
Yes, not calculated. See, there are two signals. One is the inductor current, which we are using probe to view, only view. One is using probe, we are viewing the waveform, but we don't have any signal as such. And the second one is the signal, which we have connected shunt resistance and modified it accordingly.
Okay, sir. Okay.
So if you see the violet waveform, the scale is 100 millivolt and the green waveform is 2 amperes. So if I want to calculate the gain, I can 100 millivolt by 2 amperes. So
sir, probe you mean in the clamp meter, right?
Yeah, there is this current probes. Tektronix current probes. So what this probes does is you have to put a wire and you have to insert that wire in that probe. So it will take the current and it will be fed to the oscilloscope. I think in the last lecture, SAR has shown the oscilloscope waveform. So there will be a wire that you have to connect the probe so that the wire passes through the probe. So if you consider the probe will have an opening here. So you have to make sure that wire passes through this. Yeah. So if you consider the gain, it is 50 millivolt per ampere. So for 1 ampere of current, it is generating 50 millivolt signal. So it is having 2 ampere scale. So almost it is 100 millivolts. So it is around 50 millivolt per ampere. So now it is perfectly overlapping and we have all the ripple information. So using this technique only, SAR has implemented the current mode control and everything. Now we have discussed.
Sir, why IL probe has no spikes, whereas IL sensor has?
Because this
due to bandwidth.
Yes, bandwidth issues, and we are actually tapping the differential voltage and we are processing it, right? This probe is directly sensing the inductor current. So whatever inductor current is there, it will show on the oscilloscope. But now this we are actually passing through RSH. And if you see this RSH has some small impedance. And if your pole is not exactly cancelling the zero, this inductance might create some spike, right? If it completely gets cancelled, then we are getting the scalar gain. But if you do not get the exact cancellation, then there might be some inductive effect, which might lead to this kind of spikes. So someone has asked a question. Sir, I could not attend the session from the start due to some issues. Could you please upload this video in YouTube before the last date of submission of assignment? Thanks. Oh, okay. I am not sure about the last date. When is the last date? I'll be uploading it by tomorrow night or evening or so. When is the last date?
Wednesday is the last date for assignment.
Oh, okay. So I'll be able to upload it by tomorrow itself. Then you can go through that YouTube video. I'll be uploading. So these are all about non-isolated sensing because you are not using any transformer as such. But if you go to current
2 amp is the peak current.
No, 2 ampere is the scale. So you can see this box, right? So this box length, this box means 2 amperes. So this box height is 2 amperes. So this is the scale that we can adjust in the oscilloscope. We can make it 5 amperes.
So this is a ripple.
No, not ripple, the box height scale. Like if you plot in x-axis.
What is 100? 100 millivolt. What is 100 millivolt?
100 millivolt is the scale of this violet one.
Which?
And now they are exactly overlapped. So 100 millivolt of say 100 millivolt is the box of the violet one, right? So 100 millivolt of the violet waveform and 2 amperes of the green waveform are same. They are exactly overlapping. So I am saying whatever gain that we have considered. If you go into the previous slides, so by overall gain is what? RG by R1 into RSH, right? So 1 ampere of my current is equivalent to some K millivolt, right? I am getting that K is 50 millivolt from this waveform. 50, because 2 amperes is equivalent to 100 millivolt, 1 ampere is equivalent to 50 millivolt. Okay. So in the case of isolated, they use a current transformer, say with some turns ratio NP is to NS, and say if the current is 1 ampere, they might reduce it to say 1 milliampere or so. So they're stepping down the current, and as it is a current source, we need the equivalent voltage. You have to connect a resistance as shown over here. So now V out will be R into IS. And they have put a diode.
Sir, why they are using diode, sir?
So in this particular example that SAR has taken, they have put the diode so that the current will not flow in the other direction. But there exists some products like this, which is an LEM sensor. So it senses both positive as well as negative. So it does not have diode. So this example that SAR has discussed, they have put the diode so that if there is any negative voltage that will not make this diode conduct. So only this direction currents will be flown. If say the current is flowing in this direction, then the current will be in this direction, and this will not allow that. So for that purpose, they are using diode, but it is not mandatory that it will be present in all the products. That's why I have mentioned this. I'll come to this point. So for this case, they are putting it because they don't want the current to be flowing in the opposite direction. So here they'll measure only the positive currents. That is limited to this product.
Then this was. So
Yeah.
then this can be used for synchronous buck.
Yeah. Like if you are sure, like in synchronous buck, yes, current is going less than 0. But if you are sure that current is always positive, then you can use this. I'm coming to that example, this example where this can be used. Yeah, if current is going negative, then it cannot sense. So as you know, N1 I1 equal to N2 I2. So IS NS will be IP NP. So IS NS is equal to IP NP. And from this, I will get IS by IP. And my I out is R into IS. So from here, IS is NP IP by NS. So V out is this. So depending upon my turns ratio and my primary current and the resistor I have selected, my V out will be defined. Why we use isolation? Because if we want, why we are going for isolation? Because whenever we put transformation, it will isolate this circuit with this circuit. So there will be protection, and I can step down accordingly as well. So the main intention is isolation. And yeah, so let me open this data sheet. So this is one sensor, LEM sensor. So whatever wire that you have, it should be passing through this. You can see my screen, right? Hello.
Yes.
Sir, able to see.
Okay. So this will be able to take both positive as well as negative, or we have to see. Okay, I think this also cannot take negative. I'm sorry, I was wrong. So it will primary current should be from 0 to 70 amperes, and they have given R how much R.
Sir, they
minimum.
showed plus or minus 70, right?
Oh, sorry. Plus or minus 70. Sorry, you're wrong. So it can go from minus 70 amperes to plus 70 amperes. So I'm really sorry. So it can consider both positive current as well as negative current. And they have put a limit. You can use minimum of 10 milliohm and a maximum of 100 milliohm. And they have shown the turns ratio is 1:1000. So NS and primary by N secondary is 1000 or 1/1000. I know that IP NP is equals to IS NS. So IP now NP by NS is 1/1000. So IS is IP by 1000. So if I have IP to be 1 ampere, then IS is 1 milliampere. And I connect R to be, say, R to be 100 ohms maximum. Then my V sense will be 100 millivolt. So I'm just taking these values and I'm telling this, but depending upon the supply that you have given, the resistance value, we can go until 160 ohms. So for 50 amperes maximum, for 70 amperes maximum, you can go maximum of 90 ohms. So for every product, we should go through the data sheet, and then we have to understand, and then we have to select it accordingly. So they're also telling how much could be the error, all these things. So depending upon that, we should see. And this is the LEM sensor, and wire should be passing through this. So if I
That plus minus 12 volt is the secondary voltage, sir.
no, plus minus. So LEM sensor, this sensor needs a supply voltage for it to work. So the supply voltage of the LEM sensor is 12 volt. So we have to connect that such that the wire will go through this hole. So depending upon the current, now it will give the equivalent voltage.
Yeah, where
So-
we will use the supply?
So here they have 3 terminals, right? So if I'm sure they must be so here they have given. So
For plus and minus terminals,
yes.
the supply will be given.
Yes, so this is the supply. 2 terminals are supplied, and third terminal is the current source across in series with. I will be connecting this RM, which we have discussed to be 100 ohm. And as this is a current source, it should be like voltage source we cannot short, current source we cannot keep it open. So always there should be a resistor connected to the ground. Right. So this RF we are connecting, because if we keep it open, then current source cannot be kept open, so it might damage. So we should make sure that it is always resistor is always connected, whatever, and we have to follow the resistance value that they have given. What you may ask, what happens if I connect 200 ohms? So the LEM sensor might not be able to drive that much high resistance, because of which they have given us the maximum resistance. But depending upon how much gain we want, we can select accordingly, and then we can choose that particular value of resistance. So, and depending upon the temperature also, they have told how much it can give. So all the information you can find here, but I have just given some brief idea. So they have given the equivalent circuit here. So that's how it works. And the turns ratio is 1:1000, which also they have given. So this is one such example, but you can search online. There are many such products available, and depending upon your circuit requirement, you can choose that. So this is all about current transformer. In the case of Hall sensor also, the equivalent is something like this. So there is a magnetic field, and depending upon the current, the voltage is generated, and they have this Hall sensor constant into I into the magnetic density, magnetic field density. And this also is low cost, and it is mainly linear. Current transformer is also linear, and this is small size compared to LEM sensor. So Hall sensor can be come in an IC, say SOIC package. So it will be very small compared to LEM sensor, but its sensitivity is low, and range of linearity is low. This LEM sensor is widely used in AC circuits as well as DC circuits. If you see the example that we have considered, it can be used for both AC and as well as DC. So it has a wide range of usage, and depending upon your circuit. But in our circuit, we have used the non-isolated, that RSH method, sense resistance method. But it is up to the user which one they want to use. If they want isolation protection, then they can use either current transformer or the Hall sensor, and the gains will be accordingly depending upon what sensor. Again, you have to go to the data sheet and see what is the gain that they have given, how much is the maximum current that I can operate, and depending upon it. So now we have discussed till this point, we have discussed ADC architecture, DAC architecture, why we need AC/DAC like in the circuit and where they are being used. And then we have discussed about current sensing techniques, what isolated as well as non-isolated, and what are the gains and how to select the op-amps. All those things we have discussed. Now coming to the signal conditioning circuit. So mainly it consists of ADC, and why do we need ADC driver, and DAC, and why do we need DAC driver. So again, SAR has discussed different types of ADC inputs, but I am not going in detail. I am just giving summary of this. So ADC can be single-ended or pseudo differential or fully differential, and single-ended can be unipolar, bipolar. Pseudo can be unipolar, bipolar, true bipolar. Fully differential is fully differential, true bipolar, or fully differential. I am not going into the details. SAR has given the examples, what is unipolar, what is bipolar. So if you have not gone through, please go through so that you will get a better understanding. I'm just giving this because these are actually important, because in a datasheet they'll give whether the input is pseudo differential or fully differential. So depending upon that, we have to select our whatever ADC that we want, and these are all in the datasheet, and this terminology you should be aware. So single-ended, again, single-ended means like one will be grounded, so the cost will be less, but it is sensitive to noise because one terminal is grounded. Fully differential means, again, it is a differential, both voltages are not, any one of them is not grounded, so the cost will be high, and it is insensitive to noise because there is no ground connected. So this is a ADC driver.
How the polarity is defined, sir? Unipolar and bipolar?
So unipolar means say 0 to 5 volt, and bipolar is -5 volt to +5 volt. So it can go positive as well as negative, but whereas it can go only positive. I like
Okay, sir,
each
okay.
one of them hold their own definition. SAR has shown with examples, so it would be clear if you go through that. I'm not revising it. I'm just telling what all terminology is available or what all ADC inputs are available. But again, here also fully differential true bipolars. With the circuit, you will be understanding better way. I have not put it in my slides, but I recommend you to go through that particular lecture. I don't remember the lecture number. You go through that so that you will have better understanding. So in the case of ADC driver, so our V0, whatever V0 that we are sensing, it is with respect to ground, right? So whatever V0 we have measured is with respect to ground, and it is a single-handed. And the ADC we have chosen is a differential. So it needs two inputs. So we need a driver such that it will be able to drive this ADC as well as convert our single-handed input to differential. And how are we getting these? These are taken from the datasheet. These pictures are taken from the datasheet. I'll open the datasheet and I'll show you. So for that purpose, and also to drive the ADC with the sufficient current and everything, because our VIN is just a sensed voltage, right? So it needs a sufficient amount of current to be driven. So whenever we are connecting the input, it needs sufficient amount of current to be driven, so that there is a dedicated drivers which will convert single-handed input to a differential output, as well as it will drive the ADC, and how the circuit has to be connected, what the resistor values, those are all will be given in the datasheet. Now I will open and I'll show you. So this is the ADC driver that we have used, which is AD8138, and this is the pin. So it has 8 pins. So each of the like plus
Hello.
out, what is plus out, what is minus out? Yes.
Yeah. ADC is differential what we have used.
Yes.
Why can't we use single-handed?
Yes, single-handed can also be used, but whatever ADC we have
Okay.
chosen, it is a pipeline ADC, and it is a very high-speed ADC. We wanted high-speed ADC. For that ADC requirement, it is differential, for which we'll be using ADC. If it is single-handed, then you have to accordingly choose the ADC driver. So whatever ADC we have chosen, for that this ADC driver has been selected. Whether it will be able
For
to
single-handed ADC, for single-handed ADC also, we have to choose ADC driver, right?
Yes, accordingly, which can be used for that ADC, that which will give us single-handed voltage, and which will be able to drive that ADC.
Sir, here we are using an op-amp, right? This is for sensing.
This is represented as kind of op-amp, but the circuit might not be exactly op-amp.
Okay, sir, why these are two blocks? Like you are saying ADC, that is fine.
This is the ADC.
What is this before? Yes.
So this
here
is the
actually
driver.
There are two blocks.
This is the driver.
Okay. Why we need driver, sir?
See, our ADC that we have selected is a differential, and whatever V0 we are sensing, it is a single-handed. And also it needs some requirements to be driven, which the sensed voltage that we are having cannot be able to meet that requirements. For that, we need a driver, right? Like even if you see a switch, we cannot directly feed the Q to the switch, because it is having very low power and it might not be able to turn on the switch. For that purpose, we use a gate driver, right? What is the purpose of the gate driver? Gate driver takes this input and it provides sufficient voltage to the switch so that the switch will be closed. Similarly, here also we are using the ADC so that our signal is not having that much power, so that it will provide that much power, and it will be giving the input to the ADC so that it can drive the ADC.
In order to process our
signal,
signal from analog to digital,
yes,
it requires some power. That power is being supplied by the driver.
Driver, yes.
Okay, okay.
So this is the ADC circuit. So NSIM is no connection. So let us go to the ADC. So this is the ADC driver datasheet. So these pictures are taken from here. So you have to read the datasheet and understand like what is its functionality, how much bandwidth. So they have given all this 3 dB bandwidth of 320 megahertz when gain is 1.
Does the driver and the ADC comes in single IC or
No,
there
no.
will be
ADC is
different IC?
different and DAC is different.
No, sir. ADC and the
The
driver.
ADC or driver, both are also different. They will not come in single package. So ADC driver you have to buy separately, and ADC also you have to buy separately. So these are the pin description where you can understand the pins, and accordingly with that given circuit, they will be giving some graphs here, and later part they'll be giving these test circuits where they have tested everything and how it has to be connected. All these things they'll be giving in the datasheet, and using which we have to connect the circuit. So I'm not going in details. I'm just showing what are the key information and everything. So they'll be giving different circuits. See, here is the picture. So they have given what is the requirement of the resistor. So we should connect only those kind of resistors so that it can work in the way that we want. So we have to thoroughly read the datasheet, and whenever we are connecting them or making the PCB layout, we should follow the same value of resistors and everything. And how much supply it needs, say 3 volt supply. So again, we have to see what supply it can take. So it can wide range from 3 volt to 5 volts. So we have to provide it until 5 volts, and they will be providing for 3 volt its functionality may be different. For 5 volt its functionality may be different. Say here they have given VS to be 5 volt, and they have given some table, and I think for 3 volt also they will be giving some table. This is also 5 volt. Okay, I think 3 volt they have not given. So in some cases, depending upon the supply voltage, there might be slight differences. So they will be giving table for different voltages. So just to show you what are the details, and let us continue. So this is all about ADC driver, and coming to the ADC. So we are using 10-bit pipeline ADC, and it can take up to 105 megasamples per second, but our clock frequency itself is 100 megahertz, so we cannot go beyond 100 megahertz. So we have chosen very high sampling rate ADC so that we can take the samples if you want at a higher sampling rate. And there is something called offset binary or 2's complement. If you know about 2's complement, it is good, but even if you do not know, we'll be discussing in the upcoming week. So keep this in mind. So whenever we are writing in binary digital, so it can be signed or it can be unsigned, and unsigned has 2 things. One is offset binary, and the other one is 2's complement. I'm just giving you information, but the details we'll be discussing in the next week. So an input 1 volt peak to peak or 2 volt peak to peak is the analog input, and how many cycles? So here we are taking the sample, right? So 1 cycle, 2 cycle, 3 cycle, 4 cycle, almost 5 cycle. So 5 cycle. So there is almost how many cycle? 5 cycle delay. So this is the delay that we can expect. So if you sample at this point, depending upon your frequency that you are giving, it will take 5 clock cycles. So 5 T ADC. So what is the switching frequency? So if you increase the switching frequency, then the time period will reduce, but it will take the same number of cycles. We are only increasing the frequency so that the time period will reduce. Again, this is given in the datasheet. Let me open. There is less than a minute, so if this meeting ends, kindly join again. So this is the ADC. So if you see here, they have given 1 volt to 2 volt peak to peak, and so its power, if you see at 65 mega samples per second, its power is 96 milliwatt. And as I'm increasing the sampling rate, the power consumption will also increase because it is taking higher sampling rate. And again, its supply voltage is 2.7 to 3.3 volt, and it is a pipeline ADC, 10-bit ADC. So the 10-bit is a important thing, and either offset binary or 2's complement data. If this meeting ends, please join. Okay, there is less than a minute. And so they have given a table.
Pipeline ADC means like it is able to take the number of samples of a single signal, or multiple signals can be
No, single.
converted?
So, as Banerjee was asking, ours is a single input, so we can only sample a single signal. So input cannot be multiple signals, so it is only sampling one signal. And these are the other information that they have given.
But why the name parallel?
No, it is how it is being converted into the digital. Serial means we are in the case of SAR ADC, we are first calculating the Bn-1, then we are calculating Bn-2, and then we'll finally calculate B1, B0, right? So we are doing it serially. But if you consider flash ADC, there are n number of comparators. So at a single clock cycle, it will give me all Bn-1 because this operation is being carried out parallelly. And this operation is being carried out serially. So when we say serially or parallelly, it is how the bits are being generated. If the bits are being generated serially, then as the number of bits increases, the time increases. If they are being done parallelly, so irrespective of the bits, it will take the same amount of time. Only issue will be the cost might increase. So that's how we are considering these things. And these are the pin configurations and all other details that we can get in the datasheet. So again, coming back to the slide. So again, this is 12-bit DAC that we have considered, and I'm not opening it. So this is the time that it needs to convert the digital data into analog. And it has very high sampling rate, 125 megasamples per second. And the output is again a differential. And supply is +3, +5. Again, this is given in the data sheet. So it is in differential. Again, I want it to be in single-ended. So I'll use another DAC driver. So this is my DAC, and it is going into the DAC driver, and my output is coming over here. Because DAC might not be able to drive, because I'm comparing with the comparator, right? So it needs some current. So the DAC might not be able to supply this much of current. So we need DAC driver so that it can drive the comparator, and I can compare my IL with I reference. So I reference is coming from DAC, right? So the DAC will not be able to provide that much current, but this need some extra current, tens of milliamperes. So I'll connect in between a DAC driver and I'll feed it to the comparator. Again, the data sheet is given here. So if you want to refer, you can refer. Coming to the reference power stage design. So in the reference power stage design, let me change the color. We have many things. One is inductor. The other one is capacitor. And we also have gate driver. We also have MOSFET, so many things. So we will discuss about those things. I'll quickly summarize this because I'd like to show you regarding the FPGA, and these are quite easy as well as SAR has discussed. So there are different types of inductors. One is the through hole, and the other one is SMD. So through hole is different inductors. One is choke coil, another one is toroidal coil, and the other one is rod core. So depending upon their names, their shape as well as the core will change. In SMD, we have shielded inductor, semi-shielded inductor, and unshielded inductor. So it will be completely open, windings will be visible. Here it is not visible. And capacitor will also have film capacitors, electrolytic capacitor, tantalum capacitors, and multi-layer ceramic capacitor, also called as MLCCs. We are using these in our board. And these are very compact in size, and they can be used for high frequency as well. But if you see Q is equals to CV, right? So the amount of charge that it should hold depends upon C as well as V. So if C increases, Q increases. If V increases, Q increases. So the size, as if the charge increases, then the size of the capacitor will also increase because it has to hold a much higher charge. So even if if the capacitance increases, or if the voltage rating increases, or the voltage with how much voltage it should hold, if any one of them increases, then Q increases. So the size of the capacitor also increases. So this is just to give some brief understanding about the capacitor. And as I have discussed, gate whatever signal that we are getting Q, it will not be able to turn on the MOSFET because the MOSFET needs some certain amount of voltage as some certain amount of current. then only it will turn on. So it needs some current, which that Q signal cannot be able to provide. And that's why we need this gate driver, which provides sufficient current so that the MOSFET will be turned on. So we have high side MOSFET, low side MOSFET. And when we are selecting MOSFET, there is something called figure of merit. So which is RDS on multiplied by the charge. So the charge it can hold, and the RDS on. So we usually consider a figure of merit to be a product of RDS with QG, and we'll select MOSFET which has less figure of merit, which is better, faster MOSFET. So that is a figure which people use to select MOSFETs. And this bootstrap capacitor, it provides for the high side MOSFET in order to turn on this high side MOSFET. And the one
Then
gate
what is the concept of bootstrap, sir?
so we have this, right? So this VGS, let me change the color. So this VGS is with respect to ground, right? Isn't it?
You are talking about the low side, right?
Yes, I'm talking about the low side. So VG, say 0.7 or 1 volt, is with respect to ground, right?
Yes.
Yeah. So now if I talk about VGS here, this source is floating. This source is some value, which is not ground. Whenever this high side is on and low side is off, it has some voltage, right? Say V0 or some slightly greater than V0. Now my VG should be that 1 volt plus this VS, right? So my gate voltage should be higher than this VS. So what happens is whenever this low side MOSFET is on, it has a bootstrap diode. This is bootstrap diode. So this bootstrap diode charges this capacitor because this is grounded. So whenever this low side MOSFET is on, this using in this circuit. So I'll draw in this circuit. Sorry, this is shorted. So whenever this low side MOSFET is on, the capacitor is charged to VDD. So this will be charged to VDD. Now, when we are turning on the high side MOSFET, now we are coming to the high side MOSFET. So high side MOSFET. So this is open. So this is open, and this is connected. As you can see, this is connected to this point, and it has a charge of plus minus VDD. So this point is plus minus VDD. So this is connected to this MOSFET, and this MOSFET will be on. This will be going to VG. So if you consider this to be VS, my VG is VS plus VDD. So this will provide me the gate voltage with respect to source. So this bootstrap circuit provides this external VDD or VCC for the high side MOSFET. So I am supplying VG with respect to VS. So that's for that purpose I'm charging the capacitor, and I'm using this capacitor voltage to turn on the high side MOSFET. This mechanism or this architecture is called bootstrap circuit, and that's why this is called a bootstrap capacitor. Is that clear? Okay. So if I quickly go into the digital control implementation or the field programmable gate array. So SAR has shown mixed signal current mode control architecture, where SAR is giving constant reference. So SAR is giving a constant reference, I reference, and SAR is comparing with the IL. So in the same hardware setup, SAR has implemented this, and this is the hardware result that SAR has got. So SAR is giving constant I reference. So there is no, I think I have to use a different color. I'll use red color. So this SAR is using constant I reference, and SAR has implemented the code in the FPGA, and SAR is showing the result, which we'll be discussing again in the future weeks more elaborately, but SAR is just showing the working of the setup. So this is the DC supply, And this is the probe that I was talking about, which is the current probe. And this is the circuit. The top one is the signal conditioning board, and bottom one is the FPGA. And this is the power stage, and as you know, this is the oscilloscope. So SAR has shown two waveforms. The yellow one is the V0. So this is V0 and this is IL. Okay, we'll be discussing again this in the upcoming week. SAR was just showing the demonstration, but we'll be discussing rigorously in the upcoming weeks. So coming to steps for FPGA-based implementation. So first we need to identify the control architecture, and then we have to write the code and we have to synthesize the code. After synthesizing the code, like this will be done in a software simulation called ISC. So in Xilinx ISC, we'll write the Verilog code, we will synthesize it, and we'll generate the bin file. That bin file will load into the FPGA board. So for this synthesis, we need a software which is called Xilinx ISC software. So I have embedded a YouTube video link. So this software is free software. The process is mentioned in this link. So you click this link, and they will be showing the steps to install this software. And this software is needed for the upcoming week. So please install this software before coming to the next week session. And we are using Spartan 6 FPGA for this throughout the course.
Without any hardware board, the software is enough.
It is a
for us
software.
for
So
the-
software is enough to implement the Verilog code, everything, but you will not be able to, of course, do the hardware. But as far as Verilog coding is concerned, you need this software. In the upcoming weeks, I will be using this software. I'll be showing the demonstration of Verilog code, everything. So
Okay,
please
sir.
install this software so that you can also practice it in your free time. And when we are loading it to the FPGA board, we need some configuration tool called MIMOS configuration tool, which can be downloaded from this link. I have embedded a link, but this will be needed for hardware implementation. As you will be using only software simulation, this should be enough. This is for hardware. So let me write. This is a software, and this is also a software, but this is needed when you implement in the hardware. So this is the MIMOS, the Spartan 6 FPGA board that we will be using in this course. And these softwares will be used throughout the course and are necessary for implementing the digital control in hardware. So this software is needed for Verilog, and this software is needed to dump the code or load the code in the board. So the next session will be problem solving. So before that, let me open this link. So here we have all the details. So if you scroll down, this is the configuration tool. If you click this, it will download the video. It will download that tool, and then you have to install it. And all the details of the FPGA are given here. And this is the FPGA that SAR has used throughout this course, which is a Spartan 6 FPGA board, and all the 100 megahertz clock, what all input output pins it has, all those things are given in detail. If you want to go through, you can go through, but it is not available. So it is not mandatory that you use this FPGA. You can use microcontroller, you can use any other FPGA board, or if you find any other boards where you can code, you can still use it. This whatever we are showing, it is just implementation in a digital platform, but the platform is can be anything, microcontroller or anything. Only the code will be different, but the overall architecture will be the same. So let me first keep and then save it. I would like to show you the FPGA board and everything. So let me just save everything first. Okay, now that it is saved. So pin my video, I will be showing you some hardware or the FPGA board in the video. So you can see my video, right? Hello.
No, sir, we are unable to see any video.
My
Yes,
my
we are
video.
seeing.
Okay.
Oh,
So
yes, sir, we are able to.
Okay, let me remove the blur filter. So video settings. So now you can see this board, right? Hello.
Yes, sir.
Yeah.
Yes, yes.
Yeah. So if you see, I'll be showing. So it has this IC as well as here another IC is there. So the top IC is the ADC. So this is the ADC, and you can see small black color thing here.
Yes.
So this is the ADC driver, and this is the ADC. So the pins are given in the data sheet, and this is the DAC. As you can see here, it is written DAC, and this is the DAC driver. So the flow is something like this. So from here, it is connected to the power stage board. So from here, we are getting the data, and then which is the ADC? This is the ADC. So the data is going to the ADC, and then it is going into the FPGA. It is coming back to the DAC, and then from again the signals are going through this part. So these are the switches, as you can see. So these are the on-off switches. So on, off, on, off. So 3 switches are there. In order to give reference transient or load transients, we'll be using these switches. And as you can see, it has 2 boards. The top board is the signal conditioning board, and the bottom board is the FPGA. So this is the same Spartan 6 FPGA board that I have shown in that website. So using these connections, as you can see, there are pins that are going into this FPGA board. So using these pins, the digital information is going into the FPGA. And this is the connector of FPGA. So using this connector, we'll connect this FPGA board to our computer and run the code. So like this is the signal conditioning board. As you can see, there are 2 things. One is the signal conditioning board on the top layer, and FPGA board on the bottom. And using these pins, whatever digital data that we are getting will be either coming from the signal conditioning board to the FPGA, or it will go from the FPGA to the signal conditioning board. And using these pins, it will go to the power stage board. And these are some pins, extra pins, which you can use for other purpose, whatever purpose you want. So it has one single ADC, one ADC, one DAC, as well as one ADC driver, as well as one DAC driver. So this is the FPGA board. So as you can see, these are the holes. So that signal conditioning board is sitting on top of this FPGA board. So this is the wire USB to this port. So if you can see, so this is the Spartan 6 FPGA. So Numato Lab have made this board. So that's why Numato Lab, but the IC is of Xilinx IC, which is Spartan 6 FPGA. So as you can see, here are some switches. So I can click these switches, and these are some LEDs. So just to show how it is being done. So this it comes as a package. So this is a package that has been bought. So and the wire can be connected. Now this has to be connected to my desktop or laptop, and then I have to use the software, and I have to embed the code. So coming to the Verilog coding part. So Verilog coding part will be discussed in the upcoming week. So as far as this week, today's session is concerned, I will not discuss about Verilog code, but I have written 2 Verilog codes. One code is when so my first code is when I click this switch, LED will be on. When I remove my finger, it will be off. So similarly, I have written the code. How I have written the code, that we'll be discussing. I just want to show you how this FPGA code can be embedded into this board. So, and the other code, so first code is operated on switches, and the second code is, it will be like first LED 1 will on, next LED 2 will on, LED 3 will on, and it will keep on continuing. So let me share my screen. I'll show you how SAR has already discussed, but I'll also show how this has been done. So first, what I want to do is I have to connect the FPGA board. So, okay, someone has come. Okay, so let me connect the FPGA board. First, I'm connecting the FPGA board. and I have to go to my screen is visible, right? Hello.
Yes, sir, visible.
Yes,
Okay.
yes, sir.
So I'll go to device manager and I'll open the device manager. This sir has shown, I'm also showing. So in the device manager, one thing I have to see is the port. So where is my port? I have to go. So it has detected NPTEL MIMA Spartan 6 and COM3. So I have to remember this COM3. So remember that COM3. Now I will open that MIMAS tool that I am mentioning, MIMAS configuration tool. So where I have mentioned in this particular slide. This slide. So I need this MIMAS configuration tool. So I have to open that MIMAS configuration tool. So just give it a moment. I think it is taking time to load. So this is, you can see this MIMAS configuration tool, right? Hello.
Yes, yes, yes.
So now I have to select the port COM3 because this I have seen in the device manager where they have mentioned that it should be COM3. Now I have to load that file, bin file. How I am generating the bin file? I am generating the bin file by synthesizing the Verilog code. This process we'll discuss in the upcoming weeks. I'll discuss, but let us assume I have this bin file. I have to load the bin file. So I have to open, click open file, and then I have to load the bin file. So I have written two codes as I have mentioned. One is LED switch. LED is linked with the switch, and I have to select the bin file and open, and then I have to click program. So it will take some time, and it will happen. Like it will take some time, and then it will be loaded. Then whatever code I have written, my FPGA will work in the similar fashion. So this takes some time. So if you have any doubts until this point, you can ask.
Sir, can you tell me?
If you have any doubts till this point, you can ask. So this code has to run after
Sir,
this.
actually, I'm
code,
still,
yeah.
sir, apart from this, sir, whether this board, this Spartan 6 board, this Matter board, is it, can we purchase this? Is this optional, sir?
Yeah, you actually this particular board, as they have mentioned in their website, if I go to their website, they are saying that no stock due to chip shortage, and you have to wait 52 weeks or above. But this is not the only FPGA board that you can buy. There are so many other FPGA boards of Xilinx. This is Spartan series. There is a Vertex series. There is Arctic series. So there are so many series depending upon the price and other things you can buy. It is not that you have to buy. It is not mandatory. If you want to implement and check, then you have to make the power stage board, signal conditioning board, and then you can buy this FPGA, or you can also do it in microcontroller. So now it is saying done.
Sir,
right?
this.
Yeah.
Okay.
Yeah, continue. Sorry.
Yeah, I can. Sir, actually, this board we are purchasing from somewhere. Okay.
Yeah.
Similarly, that power stage board and signal condition board,
They are not
be
available.
purchased
That
from-
have been done by our seniors. So they have made
Yes.
the layout.
Yes,
and,
yes, sir.
some
That's what I'm
layout
asking,
things.
sir. Whether can we purchase from your school?
That I'm like I don't have the like authority on this. You can ask sir. I think sir has discussed in the previous session. But if sir has not discussed, then you ask sir, because he has the authority. I don't have a say in this. So you ask sir whether it is available for you or not. Sir will discuss. There will be another live session in this month as well. So you may ask sir, you may talk to sir. So now it says rebooting FPGA and it is done. So my code has been done. So I'll stop sharing, and you can look at the video. You can look at my video, right? Hello.
Yes,
Hello. Yeah. So this is the NPTEL app. Now I have dumped the code. So whatever code I have written, it will work in the same way. You can see this LED is working, blink like on, right? So I am clicking this switch and it is turning on. I am clicking this and it is turning on. I am clicking this and it is turning on. I am clicking this and it is turning on. So I have connected, I have written a code in such a way that whenever I click this switch, that LED will be on. Whenever this switch is on, that LED will be on. Whenever this switch is turned on, that LED will be on. And similarly, this LED is on. So this is the way how I have written the code. But this is just to show you a demonstration of FPGA. But you can write the code in other way as well. So let me share my screen again. And I'll dump the other code. So I again open file. I have told you there is LED blinking as well. So LED blinking bin file. I'll open. I'll click program. So again, it will take some time. And this is for blinking. So LED will keep on blinking. So that's how I have written the code. And accordingly, the FPGA board will run. So let me quickly let it happen. Then we can solve a few problems. I have put 3 problems. So like this is the process that you should do every time. So every time you modify the code, you synthesize it, you generate the bin file, you open this device manager and check what is the port number, and you open this MIMAS configuration tool and you select the port here, and then you select that file and then click program so that it will be dumped into the FPGA, and the FPGA will run in a way that you have written the code. If there is a mistake in your code, then it will not work accordingly. So you have to be sure that your code is working fine, and how to be sure that our code is working fine,
Sir,
we'll discuss in the upcoming weeks. Yeah.
sir, here LEDs are the only source of output through which we can see our code. Right?
Yeah, that is a very good question. Thanks for asking. So first I'll explain what is happening here. As you can see, my LEDs are blinking from bottom to top or top to bottom in whatever way you are viewing it. So I have written a code so that only one LED is turned on at a time, and once one LED is turned off, its adjacent LED is turned on, and when it is turned off, its adjacent LED is turned off, and it is occurring in a loop. So it is as if one signal is passing through the LED. So it is happening in that way. Now, these, as you can see, there are holes, right? These pins can also be used as an output. Say I have given some switching frequency clock pulse, FSW, on for 50% duty ratio. I have given an output here. I can only view it in the oscilloscope, right? So I have to connect this pin to the oscilloscope, and I have to view the waveform, whether it is coming in the way that I want it to be or not. But as I am showing a live demonstration, you cannot see that waveform until I connect it to the oscilloscope. So the better way of viewing, or better way for me to show you, is the LED. So I have written 2 codes for LED. One is switch based. So now here switch does not have anything because I have not written it in the code. So switch is not at all linked with the LED. So this LED blinking, this is an infinite loop. So, and it is will keep on continuing. So, but how every board needs power supply, right? So how the power supply is coming from the board using this connector. So if I disconnect it, then it will not work. So I have written the code in that way. Yeah.
Sir, in the actually the gate pulse Q will come from this pin.
Yes, yes. So if I go back,
sir,
so,
after this we need the gate driver.
Yes, so the gate driver is in the power board, not here. So the gate driver will be sitting next to the MOSFET, which is on the power board. So this is the signal conditioning board, the top one, and the bottom one is the FPGA. So the same FPGA. So these two can be removed. So the same can be. I have taken the same board, another board, so that I can show you in like independently. So this is how the code is being run. Okay, so this is just to give you or to show you how this is done. So let me disconnect the FPGA and connect back my writing back. So before ending this session, I would like to show you few problems. So one is based on the dual slope ADC. So as you know, in dual slope ADC, first we are using a V in. by RC slope for n reference time, and the height will be equal to V reference by RC with an unknown NT time. So n is how much? N is nothing but V in, say this is V in star. V in star into n reference by V reference. So this is the same formula. So whatever value I have given, if you substitute it here, I will get n is equals to n reference is how much I have given 3. V in star is how much? 10. V reference is how much? 5. So the value is 6. So n is equals to 6. And this is a say how many bits are needed to realize this number 6? How many bits are needed? How will I get? I will get log 6 to the base 2, which will be 2 point something. So I need 3 bits. So if I implement this in bit form, it will be 110, right? Because it is 2 to the power 2 plus 2 to the power 4. Sorry, 2 to the power 2, this is 2 to the power 0. This is 2 to the power 1. This is 2 to the power 2. So 2 to the power 2 plus 2 to the power 1, which is 6. So n is 6. It needs 6 cycles, and its equivalent digital number in binary is 110. So n value is 6, and the output of ADC will be 110. So 3-bit.
So here,
Yeah.
so here the positive slope will be for 3 cycles and the negative slope for 6 cycles.
Yes, exactly. Yeah. So you are right. Thanks for pointing this out. So we have turned on, like we are using this V in star for 3 cycles for known number of cycles, and then we are using known voltage for unknown number of cycles, which we want to find. So these are run for 6 number of cycles, and how many bits I want? There is this formula log 6 to the base 2, and we have to always choose the ceiling function. So if it is 2 point something, I need 3 bits. So I need 3 bits. If you write in binary, it will be 110. So the output of the ADC will be 110. So this is the dual slope ADC. Coming to the output ADC. So one thing I can do. So first it will check. So first consider V in. So it is 0.6 V reference. So first I will compare with 0.5, right? So first I'll compare it with 0.5. This is 0.5. Is it greater than or less than 0.5?
Greater than 0.6.
Greater than. So so my most significant bit is 1 now. So I have compared it with 0.5. Now it is more than 0.5. I'll compare it with what? 0.75. So is it more than 0.75? Less than 0.75. So I'll come back here. Now 0.75 plus 0.125. So I think it is 0.875. So sorry. So it is less than 0.75, right? So it should be 0.75 minus 0.125. So how much is it? I think 675, right? 0.675, right? Or 625? 625. No. Because it is less than 0.75, so it should be compared with 0.625. 0.625. Now is my voltage less or more? My voltage is less. So this is my thing. So here it is 1, here it is 0, here also it is 0. That is for 0.6. Have you understood how I am comparing? First I am comparing with 0.5.
We are taking V reference as 0.5 of V
No.
reference.
Actually, no. This is the fraction. So V in is 0.6 V reference and V out is 0.5 V reference. So it is a multiplication of V reference. I am considering only the gain.
We are taking. Sir, I didn't get that V out by V reference even in the previous slide also.
Okay, so V in is a fraction of V reference, right?
That thing is clear.
Yeah, and I'm also considering V out to be a fraction of V reference. So this is 0.5 V reference. This is 0.75 V reference. And this is 0.625 V reference. So I am comparing this Vn first with 0.5 V reference As it is more, I have fixed my most significant bit. Now it is more than 0.5. I'll compare it with 0.5
Now you are
plus.
taking 0.5 V reference. You are saying on y-axis you have taken V out by V reference.
Yeah.
But here you are taking V out is equal to 0.5 V reference.
Which means V out by V reference is 0.5.
Okay, okay.
So the circuit logic is such a way that it will compare with 0.5 reference. If it is more, then
I
it will
got the
add.
logic, but
Yeah.
I am unable to understand the picture you have depicted.
Okay, no, like we are
No,
not going into the implementation of the logic. We are only learning how it works, how it is being implemented. That is a different scenario. We are not going into that. We just want to know how the ADC works. So we just want to only know the logic, because how it is being done, that is a different thing that will go into the architecture of this thing, which is not the syllabus of this course. Understood?
Sir,
You
this
have
is a
understood?
3-bit ADC, right?
Yes, yes. Similarly, for 4-bit ADC, then it will have 4 bits. So first it will have half, then it will have plus or minus 2 square, and then it will have plus or minus 2 cube, and it will have plus or minus 2 to the power 4. So it has 4 such things. So the resolution will be 1 by 16. So 1 by 16, 2 by 16, 3 by 16, up to some 15 by 16.
0.065 will also be added.
Yes, yeah. So depending upon the number of bit, the resolution will be that much finer. Okay, so now you have understood the 0.6 V reference. Now let me go to the 0.8 V reference. Let me change the color to red. So first I am comparing it with 0.5. It is more than 0.5, right? So my MSB is 1. Now I will compare it with 0.75. It is still more. So again my bit is 1. Now I'll compare it with 0.825, right?
0.875.
Oh, sorry, 0.875. It is less. So my bit is 1. So it is 1, 1, and 0. So that is the output of the DAC. Now I'll quickly do for the last one with a different color. So last one is 0.2. So maybe I'll use a light color, which is green. So first I'll compare it with 0.5. It is lesser than that. So my MSB is 0. Now I'll compare it with 0.25. It is still lesser than that. So again, my bit is 0. Now then I'll compare it with 0.125. It is more than that. So this is 1. So my output is 0, 0, 1. So that is this logic. Say if it has 1 more than that, then I'll compare it with 1 by 2 to the power 4. Now we are considering 3 bits, so it will be like 3 bits. So I have a question, sir, why 0.125 is added? Why 0.75 plus y 0.125? So Dharmaraj, the logic is in this way that first we'll start with binary. So like the binary tree, right? So first we'll start with 0.5. If it is more than 0.5, then we'll compare it with 0.75. So now if we are going exponentially, then thing will be reduced, right? So it is greater than 0.5. I'm checking the maximum is 1. So it is greater than 0.5. It can lie from 0.5 to 1. Again, there is a less than a minute. So if this meeting ends, kindly join. So I know that it is greater than 0.5. Now I'm checking with 0.175, whether it is greater than 0.75 or less than 0.575. So it is greater than 0.75. Now I know it lies between 0.75 and 1. How do I do? Now I'll create 0.875 and check if it is lying between 0.75 to 0.875 or 0.875 to 1. So I am narrowing it down using the binary tree approach. So that's why it will be either 1 by 2 plus or minus 1 by 2 square plus or minus 1 by 2 cube plus or minus 1 by 2 4 in such a way. So from there I am getting 0.125, 0.25, 0.75, 0.875, 0.65, 625. So all these are coming from that. So I think the meeting will end.
Sir,
after that, we will continue the discussion. Yeah.
Sir, here whether we add or no, sir, actually whether to add or subtract in the successive stages, that depends on the previous stage value, right?
Yes. So here I am comparing with 0.5. Now if it is say this is a number line 0, 1. So first I'm comparing it with 0.5. So if it is more than 0.5, then I have to narrow down this region, right? So I will consider 0.75. But if it lies in between these two, then I have to consider this region, which is 0.625. So depending upon my logic, whether it is more than 0.5 or less than 0.5, that decides which value I will be considering in the upcoming cycle. So that algorithm is in such a way that it happens. But how that hardware is constructed for this logic, that is none of our concern, because that comes into the architectural design of this ADC, which we do not want. We just want to know how the ADC is being worked. Yeah.
Sir, in this 0.2 VREF, if we have the fourth bit, it will be 0, right?
No, if we have the fourth bit, then it will be 1 by 2 to the power 4, right? It will be again compared with 1 by 2 to the power 4. So it will be more than 1 by 2 to the power 4 or less than 1 by 2 to the power 4.
1 by 2 is 0.065. 1 by 2 to the power 4 is 0.065.
0.65. Okay. Yeah. So if the voltage is lesser than this, then output is 0. If the voltage is slightly greater than this, it will be 0.001. Say my voltage is 0.05 volts. Output will be zeros.
Yes, sir. Here we have 0.2, no?
Yeah, here it is 0.2, which is greater than 0.125, but less than 0.25. So it is 0.001. Because 0.2 is greater than 0.125, right? So the last bit is 1, but it is less than 0.5, 0. Less than 0.25, 0. So it is like this. So first I have checked 0.5, whether it is greater than or less than. So in this region, I am narrowing it down, 0.25. So it is greater than or less than. Now I am checking 0.125. Yeah, it is greater than that. So first time less than 0. Second time also less than 0. Last time greater than 1. This is my final.
Here, all these cases, like the V reference is very much greater than the V in, right?
V in is less than or equal to V reference. So the maximum V input voltage is V reference. So V in is always a fraction of V reference.
Okay. If it is by the reverse, if V
No,
in is greater than V reference,
if you have considered, say, I have shown you one ADC, right? Our ADC that we have used. In that, you have seen either it is 1 volt peak to peak or 2 volt peak to peak.
or 2 volt peak to
See, 1 volt peak to peak means it can go from -1 to +1, right? Right. So this 1 volt is V reference because V in cannot cross 1 reference. So whatever V in I will choose, it will be a fraction of 1 volt, right? So that is what V reference. So this V reference is coming from the ADC. Whatever ADC we are choosing, it has a maximum upper limit. So that is this V reference. So whatever input that we have to feed, it will be a fraction of this V reference because it is the maximum voltage.
Here, like 1 volt minus volt, the peak to peak is 2 volts, right?
Yes.
Okay.
Yeah, peak volt is 2 volt, but if I am considering the magnitude, so my V in will be from minus I reference to plus I reference, right? So it will be minus fraction of V reference to plus fraction of V reference.
Okay. Okay.
So yeah, I hope this part is clear. Now coming back to this part. So this part I will not spend much time. I know the formula and you also know the formula. So V naught sense is what? IL into RSH into the gain. So what is the gain? RF by RI into IL into RSH. So the gain is RF by RI into RSH. So RSH is 1 milliohm. So 1 milliohm into RF is 10 kilo by 1 kilo. So it will be 10 into 1 million. So it is 0.01. This is my gain. Overall gain. But I have asked what is V sense. V sense is 0.01 times IL. This is my V sense.
Is RF by RI only
Yeah, RF by RI.
is the gain I am saying.
Sorry, in this first case, it is RF by RI, which is 10.
Okay.
And in the second case, V sense is 0.01 IL. Now I am asking what is the minimum bandwidth of op-amp. I have discussed, okay, let me erase this off. I have discussed bandwidth actual should be bandwidth
It
given
must
by
be
gain.
10 times.
Yes, yeah, you are right. So it must be 10 times. So my bandwidth actual should be 10 times bandwidth FSW. So my bandwidth actual is, say bandwidth given is BW, by gain of the op-amp is 10. Now this is greater than or equal to 10 times switching frequency. So what will I will get? Bandwidth of the op-amp should be at least 100 times of switching frequency. So say switching frequency is 500 kilohertz or 200 kilohertz. Then my bandwidth should be at least greater than 50,000 or 50 megahertz. So bandwidth of the op-amp should be 50 megahertz. So whenever you are buying the op-amp, this should be kept in mind that bandwidth should be more than 50 megahertz. Then only the ripple information will be you can get the ripple information here.
Sir, here the bandwidth is must be greater than or equal to 100 FSW, right?
Yes.
If this is the bandwidth of the op-amp
At
given...
unity gain.
Yes, yes. Okay. Okay, sir.
So
Okay.
if I go back, okay, so this completes our presentation, but I just want to show you one thing as you have asked. So let me go back to the ADC. So this is DAC. So this is the ADC. So let me go back here.
Sir, please explain once again the parallel ADC.
Okay. So let me see if they have given bandwidth or not. Okay. So what was your doubt?
Parallel in the sense whether it is used for multiple segments or for one segment.
Parallel what? ADC.
Parallel ADC. Yes, sir.
Okay. So in the case of ADC, there is serial, there is parallel. So the input of the ADC is say V0 of T, and output is bits, say n bit, Bn-1, Bn-2, up to so on, B1, B0. So these are n number of bits. So how these bits are generated, how these bits are generated, this decides whether it is serial or parallel. So if my bits are generated in such a way that first my Bn-1 is done, next my Bn-2 is done, and up to so on, nth stage my B0 is done. So now we are doing it serially, right? So first one is happening and then the other bit is happening. But if I generate all bits at a time or some bits at a time, say I am generating few bits one time, other few bits another time. So now we are generating all in at a time, right? Parallel. So that's why it is called parallel ADC. If you come back here, first I have got this bit, and in the next cycle I am comparing and I got this bit, and in the next cycle I got this bit. So we are doing bit by bit, which is serial.
Sir, you are
So
not audible.
Your audio is not.
Hello.
Yeah, now it's okay.
Hello.
Okay, it's now okay. It's okay now.
Up to what point have you listened?
Like some parallel.
Yeah,
you
that
said. Some
SAR we will know.
Okay. So serial
yeah.
part, it is bit by bit. In parallel, all bits are, some bits are coming at more than, I can say more than a bit is coming at the same time. So if I go to SAR ADC, so what I was discussing is here, say first bit is decided, then next bit is decided, then next bit is decided. So it is following this pattern, right? So I could say first this bit, next this bit, up to so this bit. It has 3 bits. So 3 stages. If it has n bits, it will have n stages. So this is serial. Now if you come to flash ADC, it will have n number of comparators, right? It depends as 2 to the power n-1. So irrespective of n, it will happen at a time, right? At a time it is happening. But number of comparators increases. So here, this again going into from some priority encoder. So it is happening all at a time. So all the bits are generated at a time. So the functional is happening, the functionality is in such a way that all B0 to Bn are coming at a time. So the operation is parallel, whereas here the operation is serial. So that decides our architecture, whether it is serial ADC or parallel ADC. As you might have understood here, the speed is less because it is happening serial, but here the speed is fast, very high speed. But with speed comes the cost. As the speed is less, the number of comparators that it needs, if you go here, how many comparators it needs just one comparator. So the cost is less. But if you see, the number of comparators are 2 to the power n minus 1. So for the same 3-bit, how many comparators I need? I need 7 comparators for the 3-bit. Whereas here, how many comparators I need for 3-bit or for 4-bit also? I need only 1 comparator. So the cost will be less because the number of components are less. Here the cost will be significantly high. So this is the trade-off again. Speed versus cost trade-off.
Sir, how this parallel is different from pipeline ADC? That is a different architecture.
Yes. So pipeline is a combination of this as well as this. So it has 2 flash ADCs in serial. So here one flash ADC, here another flash ADC. So flash ADC is parallel, right? And now it is connected in serial. So we are neither completely going serial nor completely going parallel. Instead, we are going it serial plus parallel. So we can reduce some of the cost as well as achieve somewhat higher speed. So that is the main motive. So if you have no doubts, then we can end this session here. And for the upcoming week, please install this software, and the details are provided in the upcoming weeks. How to use this software, everything. So install this software using this YouTube link. And hello, am I audible?
Your audio is not. It is now
Yes.
okay.
Okay, I think there is some internet issue. So please install this software, and the usage of this software will be discussed in week 7, which is the upcoming week. And I will also be showing the usage. So if you have no more doubts, then we can end this session here.
Yes. Good night.
Yeah. Thank you.